Win. So, good evening or good morning. I'm Peter Song and from University of Michigan. I would like to welcome all of you attending the second workshop on leadership excellence and development education and research of statistics. Leaders in short. I appreciate your effort on sacrificing your weekend time to attend this workshop. This is a great fortunate and honor. We are able to invite 6 outstanding scholars to speak at the workshop this evening or this morning. I hope that the third workshop of leaders next year will be a in-person conference after we successfully defeat this the pandemic next year, 2021. Before I pass the host to the workshop to Professor Yingwei from Columbia University, I would ask you to mute your speaker so that there's no noise coming from the audience. Okay? So Yin, please take over the host to begin the first session of the workshop.
Okay, sure. Thank you, Peter. Hello, hi. My name is Yin Wei, and it's certainly my great honor to be in the leaders workshop for second time. And it's my great pleasure to introduce. Can people hear me?
Yes.
Oh, okay. So it's also my great honor to be able to chair the first session on the statistical method for the complex analysis. And in this session, we certainly have 3 wonderful leaders in the field. And the first speaker is Professor Jayang Shun. She's a professor, chair, and the Bernard Zhang eminent scholars in the Department of Statistics, Georgia Mason University. And Jayang certainly done a great contribution to many fields of statistics, including the image analysis, non-parametric, semi-parametric model, causal inference, machine learnings. And besides her wonderful achievement in statistics, and Jayang is also someone really working in the collection areas, pushing for many applied statistics. And she's also an example of the leaders in the field. She has been the chair. She has been the elected fellows for the ASA, IMS, and also ISI. She's also serving on the advisory committee for the U.S. governments. So without further ado, let's welcome Professor Jayang Sun, and she's going to talk about the paradigm changes for the feature selection. Jayang, I give you. Jayang.
Can you hear me?
Yes, now we can hear.
Okay. All right. Okay. Thank you, Ying, for your kind introduction, and thank you, Peter, for organization, and thank you, Heping, for your inspiration and the leadership. And without further ado, I'm going to present paradigm change for feature selection, partially based on several pieces of work jointly with my collaborator. And today, the one which I will feature most is Richard Fun, and currently is associate professor at Cleveland State University, and also one of my former PhD students. I'd like to start any talk with 3 W's: what, why, and how. What? And the feature selection is simply to find features of variables that impact on outcome. I'd like everybody to think about, what do we mean by impact on outcome? What do you mean by impact? Is it for prediction or is it for something else? So we will have that answer shortly. Okay. Now, why? And feature selection has many important applications. It can be used for finding and ranking biomarkers, reducing nuisance features that can mask, choose, or terminate a computation. It can be used for building a parsimonious or useful model. It can be used for improving efficiency in computation, communication, storage, transportation, or downstream analysis. And nowadays, we want to talk about causal inference. We talk about it, we could use it to probe causal inference, maybe suggesting, but we still need to validate it. How do we do it? When P or N are small, we all know traditional methods. We all learned regression analysis. We know stepwise procedures. When P is large, there are popular approaches. One kind is to use penalties or shrinkage estimation, such as lasso, scat, elastic net, or MCP by Tonghui Zhang. Or you use tree-based procedures, random forest. Some of you may think about deep learning. Thinking about those procedures, many of them assume that target data are within the size of memory limitation. I have worked with a lot of data, a lot of big data. Sometimes when we download from Vinci system from VA, you can only download a small portion of it. I have looked at the situation when we have agriculture data. You could have data underground. You could have data in the field. You could have data from drones. You could have data from satellite. Your P could be very large. So the ever-increasing volume of data continuously challenges this assumption. Everything you have, you can download it once for all. More importantly, I like everybody think about what's the purpose of feature selection. Do we want to predict? You predict I'm going to die, so what? But I want to know what I can do to decrease that chance, to prolong my life. I want to know what are important features that's going to have effect on my outcome. So the false discovery rate is extremely important. So for this, I'm going to suggest alternative approach called a subsampling approach. What do we subsample? Do we subsample from P features? That's the number of variables. Now I'm using variables and features interchangeably. Or do we sample from N? And here, what I like to present today is subsample from P features when P is very large. And so I want to subsample because the purpose is the following. I want to lift the power of excellent procedures for low dimensional space to high dimension. So I will work with subsamples. So I need adequate number of subsamples, not just one or two. Once I have the subsamples, I'm going to do my analysis. So I need to merge strategically those outcomes. How do we do it? If I want to scale to large dimension or large data, and literally now I have an ensemble, I want this ensemble to be simple and easy to scale to every enlarging dimensions or size of the data. So here I'm subsampling from P features, the variables. Those must be different from those subsampling from N, number of observations. Because when you have many N's, a lot of time people assume that those observations are independent, identically distributed from the same population, or at least from the same population. And so here P features, they could be correlated. They many times are different. They do not have same distribution. They must be different from bagging or boosting procedures, which you will see very clearly in the following slides. So what do we offer? We offer something we call subsampling winner algorithm. So I'm going to show a few features of those. I'm going to give you a quiz to ask you, what does this algorithm reminds you of? So first, we will try to draw M subsamples. Each has size S from those P features. So I'm going to use a base procedure to analyze each of sample. After I have done that, I'm going to select semifinalists. After I get my semifinalists, I'm going to get my finalists. So what does this remind you of? Could I get any answer from any of you? Quickly. Everyone is ignoring me.
Yeah, I think they muted their speakers.
I muted the speakers. I heard you.
People, audience muted the speaker.
Oh, okay. This probably reminds you something called the National Merit Scholars, how you select National Merit Scholar. And that's very United States centric. And when you want to go to college, those excellent students, you want to get National Merit Scholarship. And so you will, based on your performance in your local schools, and based on all the tests you have in local schools, that's like the sample analysis, then you may be selected as a semifinalist. After you've been in the semifinalists with additional criterion, you become finalists. That's the whole idea behind it, okay? So you say, okay, now that's what you have, that I give you National Merit Scholars. That's how it's done. So I said it's different from subsampling from n. That's obvious. Why is it different from bagging or boosting? And as you may recall, when you try to do bagging or boosting, you need training data sets. How do you get your training data sets? You do random sampling many times with replacement from the n observations. So this is sampling from n, not from p. Okay, regardless, once you have this capital N new training data sets, what you're going to do for each of them, you have a little analysis result. So what you're going to do if you use bagging, you aim at decreasing the variance in the prediction by averaging over the estimates from those individual learners. So because you do them separately, you can parallelize the algorithm because then at the end you do an average. But if you do boosting, and boosting aims at improving classification by boosting weak classifiers from a group of individual classifiers iteratively. So this one is not parallelizable. But for us, we are subsampling from P. So you do not have same distribution. We cannot do simple average, okay? And however, our procedure is parallelizable, okay? So what's the difference? The key thing we have is how to score each individual after the subsample analysis. So here's one, maybe I'm blocking this part. Let me move. Oh, I'm only looking at myself, so now I don't need to look at, I move that way, since I don't see any of you. Okay, so I'm going to start with the simplest case. It's a subsampling winner algorithm for large regression. This is a very simple setup. You have a p-dimensional variables. You have the n observations, and you have those independent errors. And of course, this would require data having pre-processed. Maybe you need to do a log transformation, doing other transformation before you can use this model. And here P is much, much larger than N. Then for this P dimensional beta, the parameters, and the interesting parameter is sparse. It only has small number P0 of them, non-zero. So that's a simple, very simple setup. So if we do our subsample analysis, and we're going to draw M subsamples of size S from those features, so represented by each column of those X. And then I will do my analysis. If this is regression, I will just do my least square. If I have same variance, it's least square. If I have different variances, I probably do weighted least square. So that's what I call base procedure. Then once I have done it in each subsample analysis, some features were not chosen. If they were not chosen, they get 0 for my t value. So once which are chosen, you do have a t statistic for each feature. And what we're going to do, we're going to rank all the submodels. So I'm going to pick up the top S important ones and define the score function. It looks simple, but it includes everything. So T gives you within subsample importance of each feature. So J is my J's feature. This RSSI, residual sum squares, which is 1 over square root of the residual sum squares, gives you between subsamples importance. So of course, the smaller it is, the better it will be. So of course, I will look at those ones which I only have, which is non-zero. So this is a very simple score function. Then you can rank all features from all subsample analysis as M of them. So I get R of them. Once I get R of them, then I'm going to select Q finalists from those R. And those R is smaller. I can perform my regular analysis, or I could use a little enhanced one. I do a little lasso here. I do something else, depending on how large my Q is. If my Q is not large, I can just use a very simple procedure. So in this subsampling window algorithm, we see what we have. We have S, subsample size, M, number of subsamples, and R, number of semifinalists, and the Q, number of finalists. And H and W, I put it green because it's problem dependent. And in the example I'm describing here, W is already given and H just simple least square. And simple least square, if the P is small and it's large, it's the best one you have if you have normal distribution. Okay, and a very simple procedure. So next we want to talk about how you specify those parameters. So I have S, M, R, Q. Well, S is S. I can choose my R equal to Q and the Q equal to S. So at the end, what I need to choose is most important is my subsample size S. And M, I just make it a large. And I won't talk about how to choose M, just M is sufficiently large. And how I'm going to choose the S, we can show that if the S which I choose happen to be bigger than this P0, which is the number of true important features or non-zero features in this setup, and this procedure will be consistent in a way saying that at least we will get the sample which will include all those features, and then our last step is selecting finalist, and it will guarantee that consistency. But if I don't know this S, how do I choose this? If I don't know P0, how do I choose S? Then it doesn't need you to know the P0, but if you know its range, roughly between here and there, roughly within 3 times of those, this S as a rule of the sum is fairly adequate. We also have an algorithm called a multi-paneling plot algorithm that can help you to select them. That has a similar idea to script plot for principal components analysis, and also as some of other people have done for genetics feature selections. And I know that some people have shown that in some special cases when you have mixture distribution, it's consistent. In our case, it's much more complicated because our P features do not have common distribution. Regardless, and what we have is the following. What we're going to do for each candidate S, which you don't know, you're going to do subsampling winner algorithm, then you're going to have those weights, then you can plot them. Then you have another one you can plot them for another S, is a candidate set of the S values. Then you're going to plot them in fixed scale and free scale. The good thing about fixed scale, you can tell the impact of magnitude. Free scale, you will be able to see the shape and the curvature where it occurs, and also important distinctions among the subsets. Okay, so here's the algorithm. I know it's very hard to read, but that's the actual algorithm we have. We have already coded it. We have an R package for it. Okay, So I'm going to show you examples, then I show you those multi-paneling plots, how we actually choose them. So here's the example that my P0 is only 10. Majority are nuisance features, so 90 of them are not useful. They're just zero noises. And I have sample size 80 and just pick up variance equal to 1. So here beta value is 0.1, 0.5, 1, 1.5 until 4 and 5. As you can see, if a sigma equal to 1, first two features are extremely weak. And the second and third and the fourth kind of weak because it's like in standard deviation, a little bigger than standard deviation. Then 2 and 2.5 are moderate, and 3 strong, and 3.5, 4, and then 5 are very strong. If you have a good procedure, you should be able to get all the strong features, okay? And we hope we can also go into the left direction, some of the weak features. That's what we'd like to have. So here's a multi-paneling plot in the fixed scale. So we can look at the magnitude change. Well, the S equal to 5, 10, and 20. So this one is done without assuming we know P0. And none of them look changing much, not making much difference. And this one's starting to make change. Okay, then I like to see where the elbow point might be, whether I can tell the difference. So this is one free scale. And then you see this picking up, so 3, we don't want it. But if you look at here, basically not much difference. I'm sorry, this is cut off. This is 30, that's 40, that's 50. So it looks like 30 might be a good one. So that's from multi-paneling plot. How we show that's correct. So we did a repeated simulation and see if it's done correctly. So on the left panel, it gives you the number of the times out of 1,000 simulations that captures the X number of false features. And on the right, it's percent of times that captured the real true features. So here's a 0, 1, 2, 3 until 9, 10, or more than 10. And we want those to capture no zero features, making mistake only 5% times. And with S equal to 30, that's about right. And then when we look at capturing the true features, here 2 means at least 2, 2 plus, and 6 at least 6. Okay, so you will see that our feature 10 and the 9 are extremely weak. They are even smaller than standard deviation. We don't really hope much about it. But in terms of even moderate in the size of the standard deviation with the S equal to 30, it's doing really well. So this shows this multi-paneling plot is effective, okay? So now next I want to compare those with those popular penalized procedures. So here, this is one is elastic net. That's a SCAT. That's MCP. So if we use the default parameters from those use some kind of data dependent selection of the tuning parameters. That's what they give. So you will see that we want those to be large. Okay, elastic net by default is terrible. A lot of false discoveries. Okay, and ours is about right. Then for the true feature selection, and we had to tune those methods because by default, that's what they're going to produce. And they have so much false discoveries, then they're going to have a lot more true discoveries. So the comparison won't be fair. So we tuned those based on what we have here in terms of the error rate, then we compare them. Then you will see that the best one, if you really care, is 0.3 difference is the MCP. But overall, when you go here, all of those did just elastic net, it wasn't doing too well. Okay, so that's for independent case. And you say, well, let's do random forest. Remember random forest? it doesn't do the feature selection as what we talk about as false discoveries. It tells you those are important. You have to select the following. How many you're going to pick them? Are you going to pick 10, 20, 30, or how many trees you're going to use? Okay, so that's what we have here. And clearly, if you pick 20, you're going to have a lot of false discoveries because there are only 10 are correct. And the 30 will be, all of them will be a lot of false discoveries. And even so, regardless of false discovery, let's see how many were actually chosen. In terms, you get at least 8 correct. And for this 10, you get only 0.7% correct. And then for 20, 13.7. Okay, so that's about random forest. And we also compared other situations where those covariates are correlated. We used the model in the paper in Tipshrani and the co-authors, and they have those kind of a correlation to the rho to the power I minus j. And we get the sigma equals 3, sigma equals 1. Also, one p is really small, we increase p really, really high, what's going to happen? And those need to show screening filtering, and otherwise our procedure won't work well. We did that the same way because our other procedure uses show screening filtering. So the following are comparisons, how I'm doing in terms of my time. No one tell me?
Oh, sorry, you have 4 more minutes.
Okay, I'm going to give you a summary here, okay?
That would be good.
And all comparisons and the recommendations. So good performers based on false discoveries, for those different cases, they are here, okay? Good performers based on true discovery rate, and if you tune them here, that's what we have here. So if we get them right, false discovery change, MCP is really good, but those are comparable, okay? They're not much different, but this is slightly better. Elastic net is doing really well in the worst possible situation, very interestingly, okay? And then in order to double assure what's happening, and we suggested further, actually use 2 subsampling winner algorithms and couple them and do even better than one of those, or using one of the subsampling winner algorithm or one of the top performing ones. They work really well, okay? And I'd like you to all think about reasons why that's the case, but I don't have enough time. And just summarize, because all of those, whether you use importance by Gini index or by accuracy, all of them are for prediction. They don't care about if you really was correct. And looking at this penalized procedure, again, is talking about fitting. And you just have something here, you fit it, okay? Then in terms of paradigm change, we call you to think about when we do feature selection, a lot of time we want to find so-called true ones. Perhaps we want to prevent what's going to happen. And perhaps we want to change what's going to happen to me. So we do need to consider false discovery rate. And next thing, very quickly, in terms of paradigm change, doing regression analysis is not enough for drug discovery. Because thinking about regression, you look at change of X, I don't know, okay. You don't know, you look at the change of X and Y. You just look at those particularly covariates, how it changes to the Y. You don't really think about when the X change, the other could change as well. So what we really need is something which is an ensemble, it's a network, which I'm going to just put it down here, is that once you have chosen those features at different covariates, and you need to put all of them to variable together and run this network analysis, then find this target. The one center here is one you need to look for. And that's our target. And that's another one we also did with a very huge database. And I summarize, we really need paradigm changes for feature selection. We need a new regression procedure for the P that also care about false discoveries. And once we got those, and we really need to look at it, everything together, how they interact together. That's network analysis. And also a lot of times we need multiple tools and also biology validation to know what are the true cause and what are the important features. That's all. I'm sorry, how much extra time did I go?
It's perfect
over?
timing. No.
Okay.
You didn't go even single minutes over, but I think really excellent talk. Thank you so much. I think because of time, we probably won't be able to take questions, but I do recommend, do encourage everybody, if you have questions, maybe you post in the chat window so Jayang can answer it. So, and it's certainly my pleasure to introduce the next leader and also the speaker in the field that is, it's actually the next leader is from my home department, Professor Xueqing Wang from University of Science and Technology of China. Xueqing is a professor of statistics there, and she has tremendous publication records in Annals of Statistics, JASA, and Journal of Statistical Softwares. And what he's going to talk in today is a very simple title called Ball Functions. So let's welcome Xueqing. Okay, great. Xueqing, are you good?
Xueqing, Professor Wang.
Yeah, I'm here.
Is that okay? We record your lecture. Do you allow? I mean, I'm just ask you if possible, we can record your lecture because I was too late to ask Professor Zhang for that permission. But I asked you in case some people want to watch your lecture. I mean, yes or no is fine.
Yes.
Okay, good. Yeah.
By the way, Xueqing, I think I'm going to send you the time reminder in the chat window. So if you can pay attention to it, that will be helpful. Thanks.
我提醒一下，我们他通知上说的是可以讲中文的。OK， you can choose。OK，anyway。
你们现在看见我的屏幕吗？
可以。
能看得见？
可以。
我马上全屏。
This meeting is being recorded.
来，今天我讲的那个报告呢是这个叫求函数。OK， 其实呢就是我们最近就是说在对一些就是在做这个度量空间上就是一些思考。OK， 然后呢这个工作呢主要是别人做的，我只负责卖。OK， 就是都是下面的合作者做的。OK， 就是我只负责讲。OK， 那我今天讲的这个东西呢是什么呢？就因为今天时间缩短了，就是说我们想知道的就是说统计怎么做这种 inference。 OK， 就是很多程度上呢就是其实呢我们这个 probability measure 是不知道的，但是呢我们传统统计里面是不会关心这个，因为我们有个一对应的东西跟 distribution function， 所以我们很重要的说，如果我们知道数据的，我们其实呢是想回去的，就是说把这个 distribution function 给弄出来。 OK， 就是用的方法当然就在这里，就是我们有一些方法能够估计这些分布函数啊，就是说，但是呢，实际上呢，这个东西呢，就是说，你如果是在就是说古典统计里面，这一套做法是非常的，就是非常对的。 OK， 就是说这里呢，因为我们比如说 OK， 这里面能连起来的这个工作其实很早就已经被完成了，就是比如说这里克里文口啊、可特利啊定理 OK 就能保证这个。但是呢，问题是什么呢？问题是其实呢，就是说如果在欧式空间或者希尔伯特空间这些定义的 OK， 就是这个 distribution function 的定义其实是如果超出这个欧式空间，就是所谓的线性那个线性向量空间的时候，它其实是这种线性向量拓扑空间它其实是没有的。 OK， 那现在呢，因为我们都知道，就是说有很多的就是这种数据其实是非欧数据的。 OK， 就是带来了很多，比如说 这些所谓的函数型数据啊，我们的 SPA 啊这些等等 ，OK， 就是SPD 啊这些，还有一些呢就是说乱七八糟的，还有一些就是数的这个形状的 ，OK， 就是数跟数之间 ，OK， 它其实是不可能嵌入到一个欧式空间里面，它目前呢只能够有一些办法嵌入到这个所谓的段，但是我们的问题就来了，就是说我们能不能提供一个新的就是框架，就是说就是在这种比较复杂的数据里面能够做统计这种推断的 ，OK， 然后呢具体的说就是说我们能不能只用 OK 距离，而不是用这个所谓的角度啊什么这些来做那个的？那很遗憾的是什么呢？就是说第一个事情就不太对的 ，OK， 就第一个，因为我们说了有没有这种distribution function OK， 其实是没有的 OK， 其实我应该说就我知道的是可能是很难的这个东西，就是不一定这个就是对应定理是对的 OK。第二个呢，就是说我们能不能构造出新的这种类似的 distribution function 出来 OK， 类似的。那我刚才已经在上面已经题目上就说我把那个东西就叫 ball function 了 OK。那其实呢，只用距离做的这些方法呢，目前呢，就是说其实也不算太少，就是说，但是呢，应该来说没有一个统一的这种理论呢去说这个为什么是对的 OK， 因为本身上在这个距离上面呢，就是因为有很多就是争议，但是这个 energy distance 呢，现在呢就是说跟 distance correlation 呢前面啊还有我们的 HA 就是我们 ball 啊 divergence 啊跟 ball correlation， 所以这个还有一个叫 graph based 的 method OK， 因为 graph based 的 method 很自然的，如果你只用距离的话，它可以构造出一个所谓的 matrix graph 出来 OK。还有呢，就是说在计算机界呢有 geometry 啊，就是 deep learning 啊这些东西，其实呢它都是属于 OK 只用距离啊可以就来做东西的一个方式。但是呢，这里呢就是问题，就是说我刚才已经讲了，就是说，我们能不能搞出这一些倒腾出这一些东西来，肯定是有一些损失的一些信息，但是能不能把它做出来？但我们的回答当然是比较 positive 的。然后呢，我先介绍一下，就是主要的这个度量空间上的一些概念。其实度量空间我们是比较熟悉的，就是说我们如果有一个就是这种叫做有序的，就是这个 MD 的话，什么叫做度量空间呢？就 M 叫度量空间，就是 M 是一个集合 ，D 呢是定义在它上面的一个所谓的距离，就是一个二元的，就是这个函数 OK。那什么叫做它可分啊这些等等啊，我就不一一介绍了，因为这个是跟数学分析的概念一样。那我们今天呢需要的是就是这个完备可分的这个度量空间，也一般的教科书上叫 Poly 的空间。然后呢，我们如果注意到度量空间上呢，其实呢它是没有什么简单的这种加减的 OK， 就是它只有一个很自然的诱导出来的所谓的拓扑结构，那就是所谓的球 OK， 就是这里面就以球为单位的 OK， 就是以球为基本的。那球呢这里面呢我们可以设 OK， 我这里面用的是壁球 OK， 然后也同样的就是开球啊等等这些东西，还有球面啊你都可以设出来。那我今天定义的呢就是说因为我们是要根据观测点来定义的，就是说我们一般的在就是文献里面呢有这种叫做聚集的function ，OK， 聚集的function是怎么定义的？其实就是我们是一个二元的这个函数 ，OK， 一个是中心，一个是它的半径。但是呢，半径这里面呢，就是说我们这里面呢就算它的一个概率测度，这个概率测度一般呢我这里略掉就是一个 Blair 的这个probability measure 了 ，OK。那这里面呢，这里面呢，这个对我们做分析的来说是不够的，因为 R 这里面呢，就是说我们一般只观察到 U，OK， 那 R 这里面呢，就是说半径呢其实是观察不到的，所以我们就是说能不能从点里面构造出来？那一个很自然的想法就是说我们再取另外一个点，把这个圆心当做圆心在那里，然后从圆心出发到这个另外点的距离呢，就把它当做这个 R 来做。 那这个东西主要是什么呢？很简单，但是说能不能过得去呢？就是说就是这样定义，就是说这个定义出来的函数能不能跟原来的这个 μ 是一对应的？这个是我们很感兴趣的问题，因为这个决定了 OK 这个下面我们那个图 OK 能不能做出来的那个就是那个图案能不能形成一个闭环的一个很重要的问题 OK。那其实呢，从那个 BF 呢，其实从某一种角度上来看呢，就是实际上它是一个很简单的东西 OK， 就是说我们其实如果看这个定义的话 OK， 我们就知道其实我们是任取一点，任取一个观测的点 OK， 就是说我们然后就是做它的就是另外观测的点，然后就是画那个同心圆，所以它有一系列的同心圆，但是你如果从半径角度来看的话 OK， 就跟我们以前的飞枪所做的那个东西是一样的，就是说我们在半径上是可以做一些比较大小的操作了 OK， 因为这里面半径一般的都是一个 R 加的那个定义上，所以它是有序的 OK。然后这里呢就变成了实际上如果有 n 个点的话，我就相当于有一组 n 个的同心圆，那这些同心圆其实就构成 OK 所有的一个我的这个测度的信息就基本都落在这里面 OK。这种想法呢，就是说实际上是一种跟 distribution 的想法是很不一样的。distribution 的想法其实是从负群 OK 到一个 x 这个就是所谓的就是叫做什么半开半合的这个区间的一些就是一些上的就是叫做什么区域上的一些测量 OK。所以呢 BF 呢是什么呢 ？BF 就跟 DF 不一样的地方，就是说我们这里面呢其实呢是什么呢？是一组的这个一组的这个叫做什么呀？就是一组两的这个距离 OK 所构成的这一些所谓的这个叫做一个函数的这个函数的分布 OK。然后呢，这里面呢就是说这里面一般的细节就是说你可以看得出来，就是这个是一个是两维的，这个只是一个一维的 OK。但是我们是通过这个定义的，然后它们的拓扑是不一样的。这个拓扑呢，虽然在欧式空间上它们是等同的，但是实际上前面我们说的度量 OK 跟那个区间啊这个东西其实是在这个上在度量空间上是不一样的 OK。就是说我们 BF 用的只是一个距离诱导出来的度量，这个是很显然。如果在欧式里面他们是等价的不，如果在欧式空间是等价，但是在度量空间里面他们是不等价的 OK。所以他们通过连接的，就是我刚才讲的，就是所谓的这个聚集函数来就是用半径 OK 来连接起来。所以我们做的 BF 的工作呢，就是说很多程度上呢，就是说虽然看起来比 DF 复杂，但是呢，所有 DF OK 就是那种理论 OK 跟那个我们其实呢古典的都可以用上，所以你做这一套东西呢是不需要费很大的力气 OK 去把那个 inference 就能搞出来。但是现在呢就是说我们关注的是什么呢？我们关注的是说 OK 这个刚才讲的就是说 OK 这个 BF OK 就是到底呢是能不能起这样的作用，就是说能够替代 DF 在度量空间上的作用。这个条件呢我先漏过去不讲，因为就去讨论这个条件是比较麻烦。但是呢就是说这个是一个比较几何上的一个概念 OK。我就不讲，但是我们的结果就说了，就是第一个呢，就是说，如果我定义出来的这个集合 BF， 对它呢，它如果是什么，有两个 U 跟 V OK， 这里面 OK， 然后相等，那我在一定的在这个条件下，那么我一定可以证明 U 跟 V 呢是相等的。这个东西呢，就是说这东西呢，就是说。一面呢，就是说，如果从 U 等于 V 的话，去证明这个事情 ，OK， 去证明它两个分布是一样的，是非常好证的 ，OK。但是呢，反过来其实是不是那么容易去证的 ，OK。所以我们需要一些条件。然后第一个条件其实呢，就是 能够保证其实像常见的欧式空间啊、巴拉赫空间啊，其实是有限的，这些都对的。第二个条件，我们一般用在 infinity 这种情况呢，就是去保障的。OK， 那我们呢就是说证明的步骤呢，其实呢是通过3步，通过一个比较繁琐的，就是数学分析的这个用拓扑的办法 ，OK， 去弄出来的。就是说，第一步是比较规则的这些东西，在一些规则的球上。第二步呢，就是用 Causal 的 lemma OK， 把那一些就是不规则的球 OK 怎么填充进去，然后才能够做出来。第3步就是说我们用这种就是回到这种就是回到这种 Player probability measure 上的这种性质 OK， 我们才能够把它补完成。那另外的呢，就是说，因为我们呢就是另外的一个呢，就我们也就是在这里呢，就是做了 Product Metric Space 的是什么呢？就是说我们这里面呢，所有的这个东西呢，因为我们刚才讲的，就是如果是欧式空间最开始的 EF 是定义在一维上的，然后它是用的这个 Product 的是向外推广的。我们这里也存在这个问题，如果是一个乘积空间，你怎么做 ？OK， 乘积空间我们也类似的 OK 就可以做下来，但是这时候拓扑是很奇怪的，就是说不像我们常见的，就是说是一个区间啊，一个或者说长方形的东西，它是一个球 OK 乘以一个球 OK， 这个具体是什么？就是它还是球它不是球 OK， 但是它还是球的乘积 OK。然后呢，这个也有类似的定义，我们也在一定的条件下，稍微比那个强一点的条件下，就是也能够证明 OK， 它这个东西呢是一个 distribution 呢，就是说 Jung 的这个定义出来的这个这个波方选呢，其实是跟它的测度是一对应的 OK。然后呢，证明的要点比那个稍微复杂一点，就是需要一些就是说一些这个就是叫做乘积空间上的这种Causal 的 theory OK 来做这些事情。然后呢一般的这个我们呢也同样的就是说，因为我们刚才定义的那个球 OK， 我们刚才讲说，因为我们可以把这个东西 U 跟 V 嘛就是把它代换成 OK 一个有限的这里，所以它就能够定义一个 empirical 那个波方选。这里面的要点就是说，主要的地方就是说，我们定义出来的这个 empirical 方选呢，就是你看起来是那个虽然写成一个 μ 的测度的，但是实际上它在里面呢，真正计算的时候是看 x 就是一个点会不会落在我们构造的这个 U 跟 V 的球里面 OK。U 跟 V 球里面这里面呢，如果你去认真去看的话，实际上它在比大小，就是你看这个点落在这里面是相当于它从 UK 到这个 KL 这一点 OK， 它的距离会不会比后面的这个距离来的小？然后呢，我们做完我们做呢，就是说大概的感觉呢是什么呢？就是说 empirical 波方选呢，大概就是你可以一的都可以画出来这个图 OK， 就是类似的这个 FNV 的，就我们用了很多的，就是去逼近它，大概的形状是这样的 OK。然后呢，我今天讲的就是说呢，因为就看我有没有时间，就说主要的是我们能不能证明提供这个就是说做完那个上面以后，就是说一对应以后，我们能不能提供这种类似的 Clinical Cantoni Table 的这个 property OK。实际上我们说在满足这个条件下，在满足一定的条件下，我们这里面是有的。但是这个看起来呢是比较，就是说看起来呢这里面的条件呢 U 跟 V OK， 这里面又有一个最大值呢是等于0的。这个东西其实呢是什么呢？是需要上面这么强的条件，就是来保证的，就是其实看它数数的一个就是这个在空间里面所占的这个稀疏的程度 OK。然后呢，我们知道的这些定理呢，其实呢在一般的就是一般的欧式空间里面，就是就是一般的这个 就是一般的巴拉赫空间里面其实是对 U 呢是一个 arbitrary 的这个 probability 都是成立的 OK， 但有人做呢就是说 U 呢它会变成一个叫做 doubling 的条件，就是说一个为 R 的半径的球 OK 跟那个一个为 2R 半径的球 OK， 就是说它们之间需要一个关系的，那个就条件是比较强的 OK。然后另外一些呢，就是说看一些就是曲线，所以你看一些客服呢，如果在欧式空间上呢，就是它如果是用一般的测地距离的话，这个也是对的。还有其他的一些就是这种就是你可以想象这个 Polynomial Polygonal 这个客服是什么呢？就是那种蛋白质折贴的这些东西，它也是对的 OK。还有一个在希尔伯特空间上等等，就是说它都是对的。然后呢，我们呢就是提供的就是说，如果呢它那个我们刚才有一个东西呢，就是 mu 跟 v OK 是任意的，但是呢我们只考虑如果是样本的 OK， 这里面然后有一个 R， 所以我们这里面是 ECB OK， 就你也可以得出这个比较强的指数不等式的 OK， 不仅仅是这个就是 containing 那个 Waterly 那个 containing Waterly 那个性质 OK， 然后这个推论呢，我们推到我们这里面呢，如果两个呢，就说我们这里面是可以证明它也有一个指数不等式。这指数不等式呢，就是说会比那个效益会比 Cantonio 那个 CC 的那个条件要强一点。这是第二。然后呢，后面呢我们也证明了，就是说这个 dense property 的我们这里面过程里面也有 OK， 它是满足一个高斯的过程，而且这个东西呢是covariance function呢是类似这样的 OK， 这个看起来比较复杂，但是实际上是也就是蛮简洁的一个，就跟我们一般的那个这个就 distribution function 那种性质是差不多的 OK。然后呢，这里面的这个例子呢也是跟上面的差不多，但是比那个上面要少一点，因为它条件需要的是更强的 OK， 所以我们一直在整理这些能用到哪里，就是能用到哪一种类型的这个policy 空间上 OK， 这个是我们目前关心的。然后应用呢方面呢，就是说我们有很多，因为这个东西呢，我跟和平啊跟那个其他的呢，就是说因为早期的我们就在巴拉赫空间上做过这个 ball divergence 的工作 OK， 所以 ball divergence 呢就是我们很早就有，但是呢我们一样的可以定义 OK， 就是这个叫做relative 的 entropy 这种东西 OK， 就是说我们把 entropy 的概念也放进去了，而且发现也挺好玩的，也一样的可以做得很好。然后呢，另外呢就是说 empirical 的怎么做，我们这里都有，我们目前呢就是在这个上呢都已经完成了一些工作，但是我们也没有去发表，现在就是说去单独的去发表这些。然后呢 Ball association 它是非常自然的，就是如果是在那个我们做 independent test 的时候，我们跟别人不太一样的地方，就是说我们这里面可以定义 OK 任意的 K 组的 random 就是 objects， 然后呢我们检验它的这个一般的这种不是 mutual independent， 我们是可以检验它的所有的这种 independent 的形式 OK， 然后这种东西呢这个形式呢就跟就是跟那个当年 Hofstadter 那个independent test OK， 就是那个叫做 Hofstadter D 的 OK， 就是 statistical， 其实形式上是一样的，只不过我们这里面呢就是说这里面是把它就是一个 join 的这个BD 的减去 OK， 就是marginal 的 BD 的成绩 OK， 然后把它积分起来，所以它可以检验很多比较复杂的这个事情。然后呢，我们也一样的，我们也在 information theory 上，我们也可以就是去定义 OK mutual information 这些概念。这个 mutual information 也是为了检验这种东西，他们 K 组之间这个东西是不是独立的等等。OK， 所以我们也一样的就是因为我们的那个 BD 是非常简单的，就是你只要算它的。就是算它的属数嘛，就是比较大小就完了，所以程序上的这些东西呢是 做起来呢是非常快的 ，OK。然后呢，我们呢也可以做 regression，OK， 但是 regression 呢这一部分呢，就是这是我们最新做出来的，因为我们觉得这个事情就是说，我们以前有人问我们说能不能做 regression， 我们说哎这个是可以的，但是今天好像我时间快没了，我就跳过去不讲了 ，OK。然后呢，classification 也一样的可以做，但是呢，就是在 simulation 里面呢，就是我们 simulation 的都是这种 OK 所谓的非欧的数据，就是最简单的是 symmetric positive define 的这种 matrix OK， 这个还有另外一个就是形状的数据等等 OK， 所以我这里面的模拟的一般的是像这些老连接的这些就是这种情况 OK， 但是我们等会看就是说至少呢我们看就是说我们在测试的时候 OK 比较了什么呀？比较了跟我们主要现在目前呢就是说做这一套的举例的就跟 energy 这种 base 的比较，我们所以看出来就是这种叫做什么呀？去检验两是不是它的不是 distribution function 是 probability OK measure 是不是一样的，跟或者它们之间是不是 independent OK 这里面设置 OK 你会发现我们这里面的其实是这个效果就是 table 1 L 啊跟 table 2 L 我们都能够控制的比较好 OK。然后呢，对这个形状的数据也是这样，我们也做了模拟 OK， 就是说也发现这里面呢就是说也类似的是这样的，就是效果是如果样本量比较大的时候，我们就能够做的是比较好的。然后呢，实际的数据分析呢，我们这里面呢有几个，就是说一个是老连接的这些图 OK， 就是说变化的图等等。然后你如果去用我们的办法，我们这里面不是取什么一个区一个区去做的 OK， 就是说我们直接的就是把这些老连接跟那个另外的跟基因啊这些对应起来 OK， 那我们就可以找出很多的这种信息来 OK， 就是 P value， 这个是我们大概讲的，因为时间关系我就直接跳到那个去 OK， 这个是形状数据 OK 等等 OK， 然后这是数型的，这是那个做 eye tracking 的这个数据 OK， 然后我今天呢就是说呢，我们主要给一个信息，就是说我们现在其实呢是把这个就是在度量空间上，就是这个类似就是我们叫做就是 Causal 的这个distribution function， 这个叫 Ball function 呢，就是给弄得比较清楚了。当然很多就是到底在哪一个空间上能做，比如说在流星上啊能做，我们是知道了。但是呢，在文本上，文本需要满足什么样的这个举例的话，我们还是在做这种调查。然后呢，我们呢就是在一些上呢，我们提供了一种新的这种分析框架，而且呢，我们把算法呢就是在 R 的那个软件上，我们就是叫做 Clang 的软件上，我们应该都有提供的 OK， 就说它能够同时把这个欧式的跟非欧的数据呢放在一块来做了。然后另外呢，我们也提供了就是怎么用这一些的办法 OK， 就是说，但是我现在觉得活着就是真好，所以我就是最后想说呢，就是谢谢大家，就是我们还能够就是在一起乐一乐 OK。魏颖老师，我讲完了。
Okay, great. Thank you. Thank you so much. I think that's a really very innovative and rigorous work. We only have 1 minute left. I guess we probably won't really have time to take questions, but again, same as what we did for Jayang, I encourage everybody to use this chat function to exchange your comments and questions with Professor Wang.
那个魏英，我看这个对学期的这个球的感兴趣的不少，我们下次找个机会专门让你认真的讲细致一点。
好啊，
yeah,
好啊。
I think so. Yeah, I think it's a very new idea, right? Hebing, do you want to stop the recording or?
Oh, we can ask the next person whether he allow us to. This is 华晨是吧？华晨，我也。
Right.
华晨。
好，行。
Okay, great. So
然后刚才嘉阳说那个哔哩哔哩那边那个屏幕有东西挡住了，我不知道现在是不是好一点。
或者你可以允许我们录吗？还是不可以？
可以。
Okay, thank you. Yeah. Okay, we'll
so-
continue recording. Yeah.
Yeah, screen's fine
sure.
now. When it was presented last time, there was a logo. Just take a look at it on Billy. Just remove that logo in case it happens to you. So it was blocking the middle of the screen.
我这个不知道为什么。
Yeah, so it's my great honor to introducing the next speaker, Professor Juan Lin, and from the Southern West University of Finance and Economics. And Juan is a professor of statistics, and she's also the founding head for the Center of the Statistical Research. And I'm sure everybody in China probably also know Juan. She has been a really phenomenal and inspiring figure in the field. She has very remarkable publication records, work on the many areas, including the semi-parametric survivals, high-dimensional data, and she has remarkably received all the possible honors and awards you're able to imagine, and being one of the most successful women statisticians in China. And she also inspired many young women researchers to join our field. So let's welcome Hua Zhen for her talk. Very much looking forward. She's going to talk about the regression analysis for individual specific patterns of missing covariance. Hua Zhen, I give the stage to you now.
好，行，谢谢那个文颖的介绍，也谢谢 Peter 和张老师的邀请。很荣幸能在这给大家做这个报告。我这个屏幕共享好像有点问题，这样看得清楚吗？这个
看得清楚，你要把
没问题。
行，那我就开始了。好，题目就是做一些 missing data， 其实是 block missing 类似的，但是我们这个可能比那个 block missing 更一般一点，所以有一个 individual specific pattern。然后这个工作是跟刘伟和蓝伟合作的，刘伟是我的学生，蓝伟是我们中心的老师。现在这个数据是由他提供的，然后可以给大家看一下简单的这个数据，实际上是一个小额贷款数据。然后这个当时是有很多国内有很多这样的小额贷款公司，那么目的很简单，就是因为他们这个小额贷款这个都国内的那些老师同学可能比较了解，他就基本上没有什么抵押，然后直接就是说那个你填个表，差不多如果觉得没什么问题，他们就审批就通过了，所以风险非常大，因为没有任何抵押。然后通常贷款的这些人呢，他们其实都是收入比较低的，因为他基本上就是一个额度很低的一个贷款，几千块钱，或者学生或者是一些收入比较低的人买个手机啊什么的。所以来说，这个风险其实很高的。所以对这些公司来说，他们要能够生存，很大的问题就是说，他要保证贷款的这些人能够及时的还贷，要不然他因为他全部，但是他这个利息。这个公司本身有点类似于 P2P， 它这个利息还是非常高的，所以就是因为他们因为这个风险太高了。然后现在的问题就是什么？这个公司呢，它因为没有什么抵押物，所以我这个是不是那个我看没有抵押物，所以他们现在就是当然看这个表本身，它确实有一些困难评价这个人到底是不是可靠，所以呢，对他们来说一个很大的问题。我是不是我都不知道我这个？
好，这你在第3页 ，page 3。
行，好，那就对了，对，我就完全看不见我自己，我所以不知道，不确定这个到底是不是 work。好，他们现在的问题就是什么？这个公司如果他要成功的运作这个东西，但是这个表不行，那他们怎么做呢？他们实际上现在主要的，他们花很大的业务就是说，要怎么样通过这个人填的那个一张表短的一些信息，能够真正知道这个人是不是能够及时还贷，或者他的各种在网上的一些记录，尽可能多的收集这方面的信息。 这个其实是他们一个很大的，所有这些小额贷款公司一个很大的工作量，就是说我能够基于他一些身份证、个人信息，简单的一些个人信息，能够快速的收集到跟这个人有关的一些资料信息。所以这个，比如说他在淘宝上的购物记录，在京东上的购物记录，他的电话记录，然后他的是不是他的信贷情况，在银行里的信贷情况，那就是让他通过这个东西尽可能在网上去收集。早期的话，这种信息他们也是有一些来源的，当然具体不知道怎么来。那这个例子是什么？大概这个实际上是一个比较小的一个例子。那大概上我们可以知道这个数据大概是一个什么类型。这个总共是这个表里头这个实际上是我们分析的这个数据，总共的样本就是1725个人。就表示说，这方面的信息被收集到，比如说 pattern 1，就是指的是有115个人，他们在所有平台上的信息都可以被收集到，比如说信用卡信息，然后这个第二个平台就是淘宝信息，然后第三个信息就是他的那个电话使用信息，第四个就是他的那个银行里的信用违约各种违约信息，另外有没有违约这种情况。然后另外还有一种 pattern， 比如说29个 pattern， 就是前4个平台的信息能收集到，第5个不收集到，因为它像是不可能去收集，有些信息是收集不全的。那特别就是比如说第10个这种模式，就只有一个，就是他的那个信用卡记录这个信息，其他所有的数据都是。所以这1725个人里头呢，只有110个人完全记录，其他这10个信息都是不完全记录。好，那就说如果从确实那种来说，就是大概的说，这个就是人都有确实，只有10%的人是完全观察。那么如何基于这样子一个比较零碎的数据，能够尽可能的利用这个零碎的数据，尽可能给出一个预测。那现在1700多个人，主要有这个人，这些人呢，我们现在有他们的这个收入信息，所以收入是一个很重要的判断，就是说这个人能不能及时还贷。然后呢，有如何基于这种零碎的这种信息，能够给出一个模型，然后基于这个模型，我们可以通过这些零碎的信息，对这个人的这个收入情况做出一些预测，这就是主要的一个目的。所以这个主要的问题就是说，这个缺失比例非常高，然后缺失方式各种各样，所以我们就把这个问题推到更加一般的情况，就是说缺失方式每个字都可以理解。因为我们给出这个方法也是允许你每个人都有自己的缺失方式，没有任何固定的缺失方式。那模型的目的其实就是如何基于这种零碎化的数据，给出一个回归分析。但这个问题本身大家其实很清楚，这就是本质上就是一个缺失数据的问题。那如果你用缺失数据问题，我们稍微看一下这个现有的方法，其实传统的缺失数据方法有很多种的，比如说 CC 方法，但这个问题里头 CC 方法显然不合适，1700个只有10%的人是完全观察到，所以这个肯定是很无效的。另外还有一些 computation 的方法，这个替补的方法，那替补的方法有单替补有多替补。那单替补呢，因为它有效性不是很有效，所以通常情况下用多替补的方法。那现在其实业务上他们其实很多时候用单替补方法，那单替补方法基本上在业务上它其实也就是用个 min 啊或者什么，用这个变量的 min 啊或者其他什么信息简单替补一下。如果复杂的话，基于分布的信息我们也有很多工作，但这个就比较麻烦了。另外多替补呢，这个计算量也很大，因为你90%的都有缺失，很大量的缺失。这种替补的方法，一个计算量大，另外因为太多的替补，所以这个东西本身，这个替补本身带来的这个估计不确定性，也是一个很大的问题。好，另外有很多替补的方法，它其实也基于分布的各种假定。那这种假定如果有问题的话，它其实本身带来的估计恐怕都没有 CC 好，所以我们也简单比过，效果也非常不好。另外计算量非常大。另外还有一种我们用的可能比较多一点的方法，就极大市场估计方法。这个一方面对分布有假定，那最大的问题我们发现很有意思，我们现在得到这个方法比 MLE 要好，所以这个我也是觉得有趣的地方在这里。 最大的点在哪里呢？因为 MLE 它实际上是后面我会简单跟大家讲一下。那最大的问题就是我们这里用了一个额外的其他3估计没有用的特点，我们用了数据的结构特点，所以会比这个简单的其他3估计要好。因为其他估计本身还有涉及到很多无效参数，也会空间变大，所以它的那个方差也会变大。一会儿稍微我会跟大家讲一下，跟这个为什么我们这里出来的结果会比 MLE 要好。好，另外还有一些稳健性办法，这个是做的过程中提到的，征稿人提到的，但这个方法不太适用于我们这个数据，因为它的这个对这个数据本身，因为这个方法就是比如加权的方法或者什么，那类似这种加权的方法，实际上对缺失模式是固定的，比如说你只有第一个变量缺失或第二个变量缺失。那在我们这个问题，就是说每一个人缺失都可以不一样，每一个人的缺失pattern都不一样，这个显然不太好用在我们这个办法里。另外还要值得一提一下，就是 Peter 跟他的学生做的一个工作，用联合估计方程的方法。那么他们这个方法呢，只能用于2个来源的数据，也就是说，这我们说2个平台的数据。另外呢，直接用非参，所以也有一些尾数多元非参的问题也需要克服。那好，现在我们后面我们的目的是什么呢？就是说给出一个迭代的最小2乘的方法呢。一个就是说要考虑计算有效性，因为这个现在目前这个数据实际上真正用在业务上，这个数据很大的。另外还要考虑统计有效性，因为这个数据缺失比例非常高，所以能给出一个统计上有效的估计，也是我们希望能达到的目的。所以这个大概其实就是这里的2。目的，我们可以简单看一下 ，C 就是只用了完全观察数据 ，MLE 呢，大家能听得到吗？好像我这个提醒我的网络信息不稳定。
可以，
现在可以，现在可以，对，现在可以。
其他3估计就是提到的，可以简单看一下，我们这个样本是1500，然后用设置是随机缺失，然后正态分布。那我们知道正态分布的情况下 ，MLE 是最好的，因为我们就是用那个最小2乘来估的。但你可以看到我们这个办法当然不如 FOU 方法，因为 FOU 是完全观察，所以要差一些。但有意思，我可以直接看 IS 又是第2栏跟第3栏，所有的情况下我们都比 MLE 好。那当时看到学生做这个，当时我看到这个结果，其实是有一点不相信，我说怎么可能会超过这个 MLE 呢？然后后来仔细分析了一下，那其实还觉得这个确实因为所有的例子都是这样。然后第一个情况是缺失的比例是90%，如果缺失比例是50%的话呢，我们的方法就开始接近 MLE。但是缺失比例越高，我们这个办法跟 MLE 的差别就会越大，有点意思的地方。然后这是例子得到的，红色就是蓝色就是说显著的，就是所有3个办法都发现了的，那我们也发现了。红色的办法就是红色的那些点就是总共有27个变量，红色点就是我们这个方法发现有效，但是其他方法都没有找到有效性。主要原因就是因为我们得到的这个 SD 会小于这个 MLE， 在例子上也是这样，在大部分情况下都是比 MLE 要小。那好，我们下面看一下怎么做这个事情呢？这个简单说一下，这个 Y 就是我们的 response， 我们讨论的目前这个文章讨论是简单信息回归模型。那现在我们也正在做，把它推广到广义信息模型，还有其他一些复杂一点的模型结构。PI 就是 individual missing pattern， 就是每一个人他的缺失的 pattern 都是不一样的，所以我们对每一个人的缺失 pattern 给他一个 I， 下标给他一个 I， 然后所有的 PI 指的是他所有被观察到的变量，它的那个 index 的集合，指标的集合。然后 XIPI 就表示这个人观察到的所有斜变量写在一起。XIPI 100就是表示这个人 missing 的斜变量的集合。然后对贝塔跟贝塔系数也做相应的这种分开。贝塔是全部，贝塔 PI 就是指的是第 I 个人他的斜变量被观察到的前面对应的系数即为这个就是对应的没观察到的系数。那这就是我们要用到的主要记号在这里。然后我们目前这个设置考虑是最简单的模型，就是简单的信息回归模型。 需要这样一个假定，也就是说，在我们这里头 ，pi 就是你的 trace pattern 也是一种观察数据，所以就是说基于观察的这个东西一出来是一个是有需要这样一个条件期望为零。然后呢，我们把一这个东西重新写一下，那就可以写成这个模式，因为这是一个和，所以我把对第 i 个人重新写 ，d i 个人对应的观察的数据，还有第 i 个人没有观察的数据写成这一坨，那这两个东西是完全一样的。好，那一种简单的办法，我们看这个模型，我们回归模型可以怎么理解呢？回归模型可以理解成 given 一个 xi，given xi 的情况下 yi 的那个输入。yi 的这个回归模型就写成这个东西，所以这个模型意味着我是给定了 xi 的情况下，它的这个信号部分就是我输入的给定的东西。但是现在对于第 i 个人来说，我只给定了 xi，pi 这部分是没有观察到的，所以很自然的想，我现在如果要参照原来回归模型的方式的话，因为我的 given 的 xi 是 xi，pi， 所以我们第一个想法就是说，我给定 xi，pi 的情况下。我 yi 应该长得什么样子？所以那个第三个是自然想的，就是说我现在只给定了 xi， 对第 i 个人来说，我只给定了这个东西，那我很自然就是说我要考虑这样一个模型，那就是 x 给定 xi，pi 的情况下 yi 的期望应该是什么？那长的是3这个式子，这一部分没有问题，因为 xi，pi 是我可以观察到的。那关键是这一部分 xi，pi 一把是我没观察到的，所以我如果要基于这个3这个模型，我来去算贝塔的话，那我需要知道这一部分，就是需要知道 given xi，pi 的情况下 xi，pi 一把的它这个条件 conditional mean 是什么东西？那要处理这一坨是要用3模型的关系，那处理这一坨就是有两，那关键是要处理这个东西，就是要关键处理这一坨东西。那我这个有2种方式去考虑，一个就是参数模型，参数模型这个地方就是问题，我就要去设它。对每一个东西给它设，但是这显然是不太可行。为什么？因为这个是一个参数模型，但是它 condition 是每一个人都在变，所以你要参数模型意味着说我对每一个人我都要给一个参数模型，这个显然不太靠谱。那所以可能的方式就需要用非参的方法。非参的话，我现在这个地方 condition 是一个多元的，所以那个就很自然就是一个多维诅咒的问题，所以这个非参也不太可行。也就是说，你直接从3这个模型去做，有问题了。那我们是怎么考虑呢？那我们当然还是倾向于用非参，因为参数显然不行，因为你每个人的观察数据是不一样的。condition 一旦改变，我的模型其实就改变了，所以还是会考虑用非参。非参的问题主要就是我的 condition 是一个多元的。那我们怎么去做呢？因为我并不是感兴趣所有的这些给 given xi，pi，我实际上是只感兴趣我感兴趣的方向，我感兴趣的方向对我感兴趣的方向是这个东西，对所有的 xi， 我希望感兴趣的这些东西实际上是跟 y 有关的那个方向。所以我们怎么做呢？那我不感兴趣，不是说所有的 xi，pi 我都感兴趣，我只感兴趣 xi，pi 跟贝塔 pi 合起来这个方向。所以我现在考虑既然我假定贝塔是已知的，那我实际上是感兴趣 given wi 的情况下，这个是我最感兴趣的方向。那因此我们为了考虑多元非参带来的尾数灾难问题，我们考虑 given wi 这个模型，第一个模型原始模型它的条件期望，那就可以写成4这个形式。那这个4这个形式呢就有好处了，因为这个是一个一元，所以这是一个一元非参的问题。然后呢，那这就可以去算了。所以一元非参这里全部是一些分量，但是全部是分量，我们就分开来做。分开来做的好处就是说，我在不同的界我使用的数据是不一样的。所以每一个分量，我用下面这个5这个式子来代替。5这个式子意味着什么？也就是说，对每一个分量，我都用什么？都用这些包含了 pi 以及包含了第这个变量的这些所有的观察来估计。5实际上是我们整个这个文章的一个非常非常重要的一个，比如说怎么组织信息。为什么我们这个方法比 MLE 要好？实际上5是最关键的。这个5就是一个简单的非常估计，它只是把这里头这个里头的这个整个向量写成很多分量，每一个分量用它自己的特定的东西来表示。比如说每一个分量我用的数据不一样的，我如果是估计第这个分量， 我只用那些观察，只用什么样本呢？只用它观察到的斜变量包含了 pi， 同时包含了 j 的这些样本来估计。然后因为这个 j 不一样，所以我可能对每一个 j 所用的数据也不一样。有了这个东西，好处在哪里呢？也就是我们在估计 xij 的时候，我用了这个结构的信息。因为5这个东西，那后面我可能稍微跟其他3估计来比较一下，大家就清楚一点。这个就是标准的非参了，我就不仔细在这个地方讲。那为什么我们这个办法会比 MLE 好呢？我们可以大概看一下这个东西。也就是说，为什么这个地方比其他3估计表现好？其实5这个是关键。为什么？因为 MLE 实际上是只用了这个东西，只用了 yi、xpi 这个，假定是联合分布，然后每一个人我只用 yi、xi、pi 的这个信息，给出它的这个 yi、xi、pi 的联合释然。那这个有2个问题，一个是实际上我并不感兴趣每一个 xi 之间的联合分布，但是因为如果用 MLE 的话，我需要给出 xi、pi 的xi 之间的关系，这个就增加很多多余参数。另外呢，这个地方只用了 yi、xi、pi 的信息，而我们这个地方呢，我对每一个人，我不只是用了 yi、xi、pi 的信息，我还通过5这个式子，把其他人的这些信息通过这个结构相对，因为5这个东西意味着我实际上我还是在模型1这个框架下来做的，我是利用了这个结构，然后得到5这个信息。这样子呢，我在用第 i 个人的信息的时候，我用了别人的信息，就是通过5这个式子，我用了别人的信息。所以我这个时候不只是第 i 个人自己的信息，因为是 id， 我用的时候我就只用了第 i 个人的信息，但是利用5这个东西，我也把别人的信息通过他对我缺失数据的预测，我把别人的信息也用到第 i 个人信息来，这样导致我的估计，所以不只用了这个 id 信息，我也用了这个结构的信息，那这样就导致结构会更有效一点。另外一点就是我们也不需要去估计 xi 之间的本身它的这个关系，但是在其他3估计里头，因为我是用联合分布来做的，我就要去估 xi 之间的这些相关信息。那这个不是我感兴趣，我只感兴趣 xi 怎么影响 y， 只需要知道这个就可以。所以这个也是另外一个原因。好，这个其实大概核心的点其实就是5这个东西，我用5这个东西把结构的信息给用进来，这样导致结果估计更有效。好，那后面可以大概这个其实就是我们的主要的那个想法就在这里。另外，然后这个方法基本上就这样，然后后面其实没有什么特别复杂，就是说我用这个 zi， 也就是说如果这个人是这个变量是我观察到的，我就直接用他观察的信息；如果他没有观察到，我就用刚才得到的5这个式子的估计来代它。好，这样子呢，我实际上就是把第 i 个人的所有的信息用这种方式就得到了第 i 个人的所有的这些观察。你假设，因为不知道我就用估计，知道我就用自己。然后这个地方有一个全部都用，这个地方实际上是相合性考虑。因为我们后来发现，如果我只用这个东西，我后面得到的结果的理论性质上有点问题，所以我没用这。但这2个差别其实是很小，因为在 zi-Q 它实际上只是用在 weight 这一部分。这个是跟技术有点关系，没有很大。所以这2个东西呢，这里就因为我zi贝塔现在假设，因为用刚才那个方式都替代进去，那就是说，假设我所有的 xi 都观察到了，所以那很简单，用最小二乘来估计了。那这个 zi 就是相当于我的 xi， 这里头也相当于我 xi， 只是这里的 xi 跟贝塔有关系，所以呢，我们就得到这样一个估计方程。这个估计方程当然这里头是最小二乘看起来简单，但是因为我的 xi 或者我的 zi 实际上跟贝塔有关的，所以看起来简单，这个计算呢看起来好像有点麻烦，但实际上是很简单。因为怎么做呢？我们就把这里的 zi 跟这里的 ziq 它用上一步来代替，用上一步来代替的话，那这贝塔就是用最小二乘就直接算出来。所以这个实际上这个我们的算法就这个东西。 也就是说，在那个估计方程里头，但凡这个地方涉及到 zi θ 跟 zi 里面的那些贝塔，都用上一步来代替，然后就用这个最小二乘直接来算。然后理论上我们也能够证明这个东西其实算法是收敛的。另外，这个解也能得到这个唯一性。好，这个就是简单的就来回迭代，所以计算也非常简单，就是你带进去就行了，因为全部是显示表达。然后初始值用什么呢？初始值就用 CC 方法，就是只用完全观察数据作为我们的初始值，然后迭代到收敛为止。好，所以这个计算呢也是非常简单的，没有什么特别的。然后这里是后面呢，给大家稍微说一下理论。理论其实还是一个很标准的方法，因为这里唯一是这个非参的逼近问题，就是 kernel 的方法，所以没有特别，理论上并没有什么特别困难的地方。然后有一些基本的假定，这个假定其实还是很标准的。这里唯一需要注意，这个 h 是要低估的，也就是说，因为我们现在并不感兴趣那个函数本身，我感兴趣的还是参数，所以 h 必须还是 under smoothing 才行。然后这里唯一要注意的就是这个条件6，也就是我们的这个缺失 pattern 跟你的缺失值本身，因为我们现在缺失的值是 xi， 那也就是说你的缺失方式跟你的缺失值是没有关系的。所以其实某种意义上实际上也是一个随机缺失，但是它可以跟 y 有关系，但是跟 x 是没有关系，所以是一个随机缺失，类似于随机缺失，但是也比一般的那种随机缺失要广一点，还是有点不一样，细节上讨论还好。我就这个地方不，然后我们给出了理论。性质就在这些条件下，这解是唯一的，这个所以它也是进行正态的。这里呢有两个，一个是 sigma 跟 a， 这里头分别是两部分，一部分就是你的估计带来的误差，也就是说这部分实际上是因为我的那个非参逼近带来的这个估计误差，另外一部分就是前面那部分就是因为本身的随机误差，就是模型本身的随机误差带来的，所以它的方差都包含了两部分，一部分是逼近本身在估计那个 x 缺失数据的时候会带来一些误差，然后呢本身的随机误差。因为我们这个东西尽管得到的理论性质，但是这里头实际上 d 还有这个 e 这些东西实际上都跟你的函数有关系，也就是跟我们的那个非参里头你要逼近的那个函数的表达有关系，实际上是不大可能算的，因为每一个实际上都不一样，所以呢也没有，因为每一个东西缺失是不一样的，所以实际上对每一个个体来说，你的那个function都不一样，所以这个公式是有的，但实际上是不太好算的。我们给的还是用 bootstrap 的方法，理论上我们也证明了，这样子你用反复抽样的方法得到的结果，它重复得到的这个 bootstrap 的估计，能够逼近那个真正的那个方差。
华正 you have 2 more minutes。
好，行，那我把模拟简单说看一下，这里头就我差不多了。然后我们模拟就是用50%缺失跟90%的缺失，然后也做了2种测试，一个是完全随机的缺失，另外就是因为我们刚才讲了，我们要跟 x 独立，但是允许我跟 y 是有关系的，所以呢，这个跟 y 有关系，所以并不是完全随机缺失，做了2种设置的情况。然后有 epsilon 我们一个是正态，另外一个是混合的，两个正态的混合。大家可以稍微看一下，这个就是说，基本上我们的这个结果就是一个，刚才其实已经给大家秀了一下。这个就是说也是正态，这个是随机缺失，结果类似。然后我们也对这种非随机缺失正态的情况下，大家可以看到 MLE 是非常差的，也就是 MLE 对随机缺失是一个要求，还是要求它是一个随机缺失。如果是像我们这个跟 y 有关的缺失 ，MLE 就不行了，所以它那个 bias 是非常大的，在这种情况下 bias 是非常大。然后这个是 mixed normal， 因为我们知道正态的情况下，我们是用最小2乘的方法做的，因为假定是正态。然后现在如果是 mixed normal 的话，这个 MLE 也不行，因为它对分布是敏感的，这个大家也可以大概看一下。那所有这些情况下，我们的表现还是非常稳定，没有很大的波动，对那个分布、对缺失的方式都不是特别敏感。 好，然后这个地方就检查一下呢，我们用 Bootstrap 的标准估计方差是不是合适？基本上还是 reasonable。哦，然后这个就是数据，数据大概有27个变量，有各种平台，每个平台大概其实有3到7、8个这种变量，所以有5个平台，大概就是27个变量这个样子。好，这个就是每一个变量之间的相关性，因为这对我们问题来说，其实相关性越强，我们这个方法应该会表现会好一些，因为我们实际上是完全利用变量之间的关系在做。然后这个例子结果本身也给大家刚才看了一下，哦，然后这个是例子，也，所以这个大概说这个方法呢本身就是现在目前为止在做在细节回路模型，我们现在也正在做这个，把它推广到更一般的模型、广义线性模型，或者那核心点就是说，就是怎么样更有效的利用数据结构，可能是一个非常重要的一个信息。好，谢谢大家。
Yes, thank you, Juan Lin. It's perfect timing, and it's a really great talk. I might use my chair privilege, ask just one simple questions. We're using those kernel more because the equation number 5, which is the key of the method, because often when you use a kernel approximations, it could be sensitive to the dimension of the data. There's a method. How many? Like I guess what's the date? Is a method sensitive to the dimension of the missing data, missing variables?
No.
It's all you do one at a time.
你说是那个 dimension 指的是 x 的 dimension 吗？
Right, it's a dimension of the x, because the equation is a kernel, right?
对，因为我们是这个点，我们实际上就是一个 one dimension 的飞参。
哦，是一个一个做 IC。
对，因为这个地方你看，这个实际上是这个东西，基于这个东西，这个 WS one dimension 就是我们的点。
就是
这个是最关键
的。是一个做 IC。
对，
basically a single index somehow like index.
Gotcha.
文莹，我能趁机问一个很快的问题吗？文莹。
哦，可以。
正好因为林老师在这个 slide 上。
报名，谁问问题请说名字。
就是sorry， 我是朱记，对，你好，林老师您好，那个对，非常有意思的 work。我就是一个正好，因为刚才韦老师问了一个问题，我就趁机在这里问一下。就因为你这里面你这个那个求和呀，这个式子里求和是要求那个 pi 撇它要包含这个 pi 和 j 嘛，对吧？
对。
那个如果有很多 missing 的话，就因为刚才您说的那个 missing， 比如说90%都是 missing 的话，那我这个求和里面就是满足这个条件的这个 i 撇这个 pi 表，它是不是会很多嘛？是不是会？当你 missing 很多的时候，是不是会很少啊？这个满足这个条件的 pi 撇。
但是我是每一个分量分别去做，当然也是你如果说都特别完全没有的话也没办法。实际上我们这个式的这个 xij， 也就是说还是要有一定的那个 sample size， 也就是说那个 pi 一撇包含了 pi 交叉级那个并集，这个要有足够的量，要不然我得到的 xijp 不能满足我的条件。就是我有一定的条件的，所以这个东西还是要有一定的 sample。如果完全没有，如果很少的话，也是个问题。但好在哪呢？因为实际上我是 xij 本身，我实际上外面还有一个 average， 所以即使说某一些 xij 上我估的不好，我其实可以通过 average 的方法，还是可以把它缓和过来。
OK， 好，行，谢谢啊。
Yes, it's a wonderful talk. Because we're a little over time, so it's just to thank all the speakers for their really inspiring talk. It's a great way to spend the weekend here. I think now I'm going to pass on to the next session. Peter, are you going to be the chair for that?
Yes.
Okay, great.
Yeah, I will chair the next section. That's new developments in machine learning and optimization.
So right, that's a no break.
No break. Yeah.
你那个等一下提醒下面的人，你让他们25分钟到28分左右就停下，这样呢就大家可以讨论一下，对。
Yeah. Well, they prepare a lot more slides than being covered by 30 minutes, right? So but anyway, we will have 3 talks, and so maybe we just jump into the the first talk of the second session. The next talk will be given by Professor Hansen Wang from Guanghua School of Management Science, Peking University. And Professor Wang doesn't need really an introduction, right? He is a leading researcher in statistics. He's so well known in statistics community in China internationally. So he has made a lot of important contributions in statistics. So just for the sake of time, I just probably let Professor Wang to start his presentation. He's so well known. So please go ahead.
Okay. Recording continue.
Yeah. So
no
Hansen,
problem.
do you
want
us to do you give us permission to record or now?
Sure, no problem. Do anything you want.
Okay. Good.
Okay.
Thanks. So we continue recording your lecture. Yeah.
Okay. Well, thanks, Peter, and good morning and good evening, everyone, and also thanks, Heping, for the invitation, and thanks everyone for the time sacrifice. Happy weekend. And today I'm going to share one of our recent progress about deep learning, and it is something about the learning rate.
Hi, Hansen, you're still with us? Uh-oh.
那边效果有点问题是吧？
Uh-oh, we lost Hansen.
when we lose him, maybe is he the guy called Shun?
Yes.
Yes.
Who is Shun?
No Shun.
Next speaker.
Next speaker is Shun. Okay. Hongtu is the next is Shun.
I'm just kidding. Maybe that's the question you should ask the speaker.
No, Xiong, I know who's Xiong.
How did this Xiong
I think Xiong is 长项语.
Oh,
actually, there's a famous cartoon. It's called Xiong.
What's the story behind it?
熊大熊二。
那我们是等汉森还是让宏图直接上呢？
让宏图讲吧。
OK。
宏图 ，Are you ready to go？
是不是等一等真的
Okay, we can switch
the order of the two talks.
Yeah, we can switch the order.
Okay. I'm fine. I know this is not. It's terrifying with me.
Yeah, I don't know how to stop his screen sharing.
You're the host.
Yeah, I'm the host.
你怎么暂时把他的 co-host 给废掉不就行了吗？
Oh, that's good idea. Just turn off the power, right? Then you can reboot. Oh, this is quick dirty trick, right? So let me just.
好多中国的网线好像是有点。
这个是网有问题。
Yeah， 华真的不错啊，没有什么问题啊。
所以我今天但是我
有点问题。
刚才早一点的时候被踢出来几次，是有点问题。我还幸运刚刚能顺利讲完。
你们开始，我跟汉森打个招呼，我告诉他一下。
Hongtu, can you go to share your screen and to override his Hansen screen?
I can do that.
Give it a try.
No, it's okay.
I cannot see your. I cannot see your slides.
Really? I think there's some. It doesn't allow me to share it.
Oh, it does not allow you.
你那组只能直接把它强制掉。
Okay, now I got it. Hongtu.
对。
That's your yeah. Okay, we probably switched the order of the speakers, and so Hansen has some technical difficulty at this moment. So we switched to the second talk and by Professor Hongtu Zhu, and so Professor Hongtu Zhu is another well-known researcher who doesn't need really an introduction either, right? He has made many important methodology rich contribution to statistics. And I'm so admired him because he's one of the pioneers who moved from statistics to sort of the artificial intelligence. And he joined DD Tuxing, right? And as a chief data scientist and working on a lot of practical problems. Really with the big data and applications, important applications. So DD Tuxing has given him a very challenging venue to work on a lot of interdisciplinary problems. And I'm very happy that he agreed to give a talk tonight. And so that we will see what he's going to talk about his work in related to transportation and this big data. Yeah. Okay, go ahead.
Okay, thanks, Peter, for invitation. Actually, it's the last minutes, and he invited me to give a talk. Actually, I didn't prepare anything because of the busy schedules. And I just pick up the ones the talk I gave in last several months and about two-sided markets. And actually, this slides is developing, keep on developing because we have every month we have some new results and we add insight. Okay. And actually, one thing is when I started the job at the DD, one question I asked myself as a statistician, how much I could contribute to the company in what sense. Okay. And actually, we struggled a lot at the very beginning, and gradually we found that the statistics could make a big impact in the IT, in particular e-commercials, this kinds of business. That's the reason I want to share some of the insights from the lessons I learned in the last 3 years. One big thing about AI success or the machine learning success, I think the success is mainly due to the data itself, okay, application itself. I think if you, in these days, and actually Michael Jordan actually gave it in the last 3 years to keep on talking about something related called AI successes. Actually, he summarized these kinds of 4 periods. The first one is between the 1990 to 2000. It's mainly about search fraud detection, this type of problems. And the companies use various statistical methods like random forest to reduce the fraud detection rate. The second generation is between 2000 to 2010, and they focus on recommendation system and social media. And actually, it's still one of the most important kind of systems these days people use. And actually, they try to develop an effective product recommendation engines, and in many kinds of e-commercial companies, including Amazon, Alibaba, and eBay. The third generation is still related to application itself, is from 2010 to now. It's mainly focused on the speech recognition, translation, and computer vision. And actually, people are developing various deep learning-based models to mimic human intelligence. But I think so far is far from the human intelligence, okay? And the first generation, that's important. I think that's something I realized that even I spent most of my career in medical science, but I think these days and the people think about how much we can do and in next generations. It's not about deep learning itself, it's about the application itself. We call it this application the first generation is an emerging one. You focus on various markets, including clothing, food, housing, transportation, education, Medicare, and nursing. And actually, these kinds of markets, and actually people use the intelligent things and cloud computing to connect to customers and the products together. They try to produce and new commercial platforms like Uber, Didi, eBay, all kinds of platforms. And it involves multiple agents making a sequence of decisions and actually leading to the improvement of customer experience and efficiency. And that's the things I think the statistics will play a critical role in insight. That's the one thing I learned in the last 3 years. And what is the two-sided market? It has been in the economy for a little while, and the two-sided markets are roughly defined as markets where one of several platforms enable interactions between end users and try to get the two sides on board by properly pricing each side. And here are several examples of two-sided markets, including Airbnb and eBay, and Uber and Amazon. And for instance, Airbnb is a two-sided market with hosts in one side one and then travelers inside two. And the ride-sharing platforms is also a two-sided market with customers inside one and the drivers inside two. It's a very complex spatial temporal ecosystems. That's happening for most of these markets, two-sided markets. The relationship between the customers and the drivers is nonlinear and interactive. Such a relationship is uncertain due to the influence of environment and other factors. Is also a complex causal relationship, as we'll detail below. And actually, in last several years, and actually I work with a group of the smart people, and to develop this kind of method called basically, we try to solve the problems, and try to evaluate and improve the operation efficiency of the ride-sharing platforms. And at the very beginning, and actually I don't know which problem I should start with and how to solve it. And actually, we find our final goals is to develop an AlphaZero, okay? It's a simulator in order to achieve these goals. And actually, at the end of, until right now, we can class all the kinds of methods, all kinds of the topics into the 5 different major research topics. And actually including the, one is the supply and demand forecasting. The second one is supply and demand diagnosis, and also the policy assessment and the policy optimization as customer lifetime value kind of analysis. But for all in order to achieve all these things, and actually we'll have to use a lot of statistical knowledge, like experiment designs, deep reinforcement learning, spatial temporal modeling, and graphical models. And actually that's what we find that statistics play a critical role inside. And the first problems we try to solve is basically the supply and demand forecasting. This is also happened for almost all these kinds of different e-commercials. Basically, what is your supply side? What is the demand side? How to predict this kind of thing. The problem we're trying to solve is basically we try to predict the demand and supply distributions, and basically, and we have to integrate the information and across the different domains, and that's the, and also we have to account for the complex spatial temporal patterns. And actually, when you try to do these things, we also do the transfer. Basically, we need to do heterogeneous space among the cities and heterogeneous features among the tasks. And also the most important things we need to do basically causal inference in model, increase model interpretation, impact analysis. Because when you do the forecasting, and actually most of the people think we don't need the statistics, but it is a pure machine learning problems. But we find at the end of the day, we find that the causal inference is critically important, because when you try to develop a forecast system, at the end of the day, you have to solve the real problems, okay? You wanted to basically manipulate some factors basically and change it, and so that you can see the change of the supply and demand in a certain way you want. And actually the goal is to try to improve the service quality from driver side, rider side, and platform side, okay? That's the basically forecasting is not just pure forecasting. At the end of the day, we still wanted to have a system so that we can manipulate in a certain way to help the, both sides, both the driver and the rider side. And this is just when we started the project. Actually, we started with how to predict basically the demand side, and basically the foresee the future orders, and actually you can prepare for future peak hours, dispatching vehicle for regions with high demands, and do a lot of other things. Then the good thing is because if you really know the demands, and actually that empowers better strategies and the services. That's very important in practice for the company. And actually, when we started this project almost 3.5 years ago, actually, how to do this kind of project. Actually, it takes a little while. You see, we have 4 or 5 papers along these lines. The first one, we build these kinds of the graph structures, because these big cities, they have special temporal patterns. You have to generate the graph so that to simplify the problems. And also we do the temporal kinds of the modeling, and also do spatial modeling, so that you can see that how to first you need to build a kinds of the basic structures for the modeling. The second, this is basically the different way to characterize the spatial dependency. We have to go beyond a simple labyrinth relationship, go to the like a rotor connectivity and the POI similarities. And we try all kinds of methods, and of course the deep learning method works better in this sense because it's more flexible, but it's just computationally more costly. And also we in the last 2 or 3 years, people use a lot of transformer and this kind of the trick, because that's the fun NLP. And actually that's the good things, because we can use this like a spatial temporal transformer to handle the spatial unsmoothness and the temporal unsmoothness. And actually, we have this kind of we integrate the spatial temporal attention plus and encoder and decoder, this kind of thing, to solve these spatial clustering and temporal calibration. And also, of course, this is better than existing method in certain way, and then achieve about 10 to 25% of error reduction rate. And actually, and earlier of this year, I asked my folks the questions, and then even though we can predict just the demand, how about we predict both the demand and supply together? And also we want to predict the demand completion rate, because that's important for company. And in order to do that, because these 3 things are highly related to each other, it's not a simple correlation relationship. Actually, for company, the most important part is the demand side. Then you have the supply, and also then you have the demand completion. And we have this is sequential relationship. Another thing that we think about it, because the forecasting systems, actually there's a lot of factors is the kinds of environmental factors, and also there's some factors related to company itself. And the question we have is, how does this factor from the company side influence the kinds of the supply and the demand completion? And that's something we want to do, because that's critical for company to make the profit, because then we wanted to improve the service to our both the customers and also the drivers. That's the reason they force us to go to the causal inference, other than a kinds of a black box, kinds of the forecasting engine. That's not something we want, because at the end of the day, we really wanted to tell the kinds of what kind of strategy we can do to make it the forecast to better in certain sense. Okay, and that actually that's the one thing we try to do in this year, and actually we put a lot of effort to try to incorporate kinds of causal inference framework into the existing supply and demand prediction problems, and also try to map them. And this is basically one of the examples we did. And for these, like in 4 different, the first one is rainfall, the second one is mid-autumn, the festival, and there's a National Day and the Chinese New Year. You see that the prediction is relatively good in certain sense. And also we did apply it to different cases, and to see to do these kinds of, we wanted to do online kinds of prediction. For instance, I wanted to predict the next 10 minutes, how does this kind of varies. We want to do these kinds of predictions in practice. And another thing that we did is for the supply and the demand diagnosis. And why this is important, then because in the companies, because the most important thing is not the GME itself. Okay, it's not just the driver's income. The most of the factors we find that the most important thing, basically we wanted to satisfy both sides, because if one side is not happy, they will leave the platform. Therefore, basically, instead of direction model optimize the drivers, the incomes, actually we try to think about how about we match the demand and supply in certain way. And actually we tried to basically come up with a metric to quantify this kind of the relationship. And in practice, we developed kinds of this kind of new metric called the graph-based equilibrium metric. Well, what's this useful? Because we want to quantify this kinds of supply and demand in imbalance. Because when this is one extreme example, you have too much, demands. This is another example. You basically you don't have enough demands. And actually, this is the kind of we don't think. We personally, when we started with this kinds of analysis, most people just started with GMV, this type of the this type of the metric. But I think is not quite right, because we think we needed to focus on the supply and demand balance in a certain sense. That's the reason we have these kinds of papers that started about 2.5 years ago. One of my students did most of the work. This is the initial distribution of the supply and demand and in a graph. Then the question is because for these kind of transportation problems, and you cannot directly calculate the differences because the drivers can move. That's the reason you can do this optimal transport. Okay, you need to transport the drivers in certain sense. Then after transport, then you see that there's the kinds of agreement between this demand and the supply side. Okay. And actually, this kinds of when we define the graph, you can use in different kinds of the size of these kinds of hexagon. And actually, we can, by varying these kinds of the size of this shape, and actually we can get to the multi-level representation optimal transport functions. Because in the company perspective, and we wanted to, because this optimal transport function is associated with the company's strategies, like how to dispatching the drivers and all these kind of things. That's something we wanted to see. Okay, and this is the mathematical behind this stuff. And actually, this is essentially we goes to this unbalanced the optimal transporting problems, and we solve it by using an LP kinds of linear programming to solve it. Okay. And actually, we compared basically the first thing. So we're using different metric. We use this information to do predictions. We achieved a much better prediction accuracy compared with other metrics. And also, this is the key, because the whole these papers we say that we define the imbalance between supply and demand. Okay, that's the most important metric instead of using GMV, this kind of money type of things. And because we think that we needed to have the better environment for both the demand and supply side. But in practice, actually, this is important because we want to do online the demand and supply the imbalance quantifications. Why this is important? Because at the time t-1, I have demand and also my supply. And I want to calculate the supply and the demand mismatching, because if I have at the same time I have my micrometric like money, the GMV type of this kind of policy, this kind of values. Okay, the global value metric, micro the metric. Then when you're looking at these kinds of the statistics and all these maps, what the question is how the company need to do something. Okay, and if there's a bigger mismatch between the two sides, we need to try to solve the problem. Okay, then we have the policy guess up, and actually we go to the next time point, and actually we have the new demand and the new supplies, and see basically we continue to have these kinds of sequential, this kind of time series type of the observations. So that the question is, how do you first you need to do diagnosis in the sense of you need to look at these kind of patterns. The next question is, what are the optimal policies you can use to minimize the imbalance between the supply and the demand side? That's the most important part for this. Okay, and this is basically the platform that we developed, and actually with help from other people in the company, and actually the most of the that's the underlying all these calculations, many did done by our teams. The next question is basically when we looking at the data, right? The next question, how to optimize these kinds of policies, because in companies we have the various different policies, and this is basically that's the way we did. And the question is goes to the next, when you have a diagnosis, the next question is how much you can improve the in platform policies in order to optimize the key micro metrics. Okay, and this is very important, and this is, and actually we have to go to use the reinforced learning to do that. There's a lot of success stories of using the reinforced learning in the chess or like, and all different games and AlphaZero, AlphaGo, this type of things. But these days, actually, there's more application try to use reinforced learning, like precision medicine, recommendation system, transportation, industry controls, and other things. And this is the some of this basic notation about MDPs, but just to give you some ideas of the states, action, the transition, and the reward and the discount. And for MDPs, there are two. This slide is one of the most important slides. And actually, this is basically you'll see the sequential kinds of the state action, and this is the observed data. If you suppose sometimes they are missing these observations for this state, and also you have next stage, and also next observation, next action, and you see the sequential actions. And also at the same time, so each kinds of state you get a reward. Okay. And actually, you can quantify the joint distribution. You can just ignore this reward. You first you write the joint distribution, all these states and the actions, and answer the joint distribution of this. Okay, you can use this sequential rule to do it. And the most important things, and actually that's controlled by the policy makers, is this pi. Okay, the pi theta. Pi theta is basically the given the state I want to make an action. Okay, just like you have the treatment. I give just like a person who basically has certain treatment symptoms, then I give you a new treatment. And actually, this is the most important part. Companies do the same thing. And basically, for the ride-sharing company, I have this kind of the supply and demand in mismatch of imbalance. And then the problem is, how do I change my policy in a certain way, basically, and make these things better. Okay, that's the most important part, because for all the MNTPs, you have this in your object. You want to optimize them. That's your observed data. Now, at the same time, you have reward, because you're not just interested in doing like a statistical modeling, because that's important, but that's not our object. Our object is to optimize the state like a value function. Okay, or like the two functions, and actually they have these Bowman equations to characterize their relationship. Okay, and actually in MDPs there are two kinds of problems people are interested in. One is called prediction problems. Basically, you're giving a policy, you input the MDPs and the policy, and you output the value functions. Okay, but there's another control problem. Control problem is actually we wanted to search for the optimal policies. Basically, your input and MDPs, your output the optimal value function, optimal policy. That's the basically called control problems. And actually, this is that's why you have these kinds of optimal policy. You wanted to optimize that. And actually, in the last 3 and 4 years, actually, one for our team is mainly working on this reinforced learning kind of thing. And actually, at the very beginning, we do a lot of things for these kinds of dispatching. Then this year, we focus a lot of effort on the disposition, and also we do a lot of other things. We also focus a lot of on kind of incentive, other things in the company. Because for both the customers and the drivers, because right now we need a lot of drivers in the platform to hold the number of the requests demands these days. Okay, there's something nowadays actually reinforced learning has become a standard method in all these kinds of the research teams in the DD. Okay, and actually that's one of the things people want to try, because we are looking for more like a long-term profit, and that's the most important things. And actually, for one of our strategies, we serving in the DD's online production systems is active in top 20 cities in China, and 1 to 5% of the increase. Okay.
Tutu, you have 5 minutes.
I know, and that's basically one of the awards we got last year. And actually, this year we are focused on repositioning, and actually, And this is basically, we have a lot of different test, online test policy kind of evaluation for that. Okay.
洪都，这是你故意放给我们看的吗？
对啊。
OK。
Can you hear it？
没有声音。
没声音，这是为什么我问你？但是顶翻是图像顶翻词，对。
没有声音是吗？
对。
Who is playing?
This one. Yeah. And actually, this last part actually has 2 more sections. One is basically related to the policy evaluation. It's for statistics, we know that one thing is A/B test or related to clinical trials. And actually, in the platforms, one thing we need to do is how to evaluate platform policy by comparing different policies. Okay, you have the policy 1 and policy 2, how to compare them. And actually, this is the problem is a challenge because this is the first one we have this kind of stronger interference because the drivers and also the customers and actually the highly correlated with each other in the sense of the drivers are competing for the customers and also the reverse. Okay, at each spatial temporal location, and also the larger variation key metric. And actually, external factors have much larger influence on this the variable of interest, but the internal factors only influence a small amount. And also there's an interaction among the different policies. Then this is what we did with my student, one of my PhD student. We did this stuff. Basically, we have 5 different categories like scenario control based method, observations method, up-to-infinite for the modeling, multi-armed bandage, and MDP type of things. Okay. And this is some of the work we did recently. Basically, one is basically to covariance adjusted randomization, and another one is doing temporal experiment. And actually, we compare the 2 different policies by using the reinforcement learning to do it. Basically, these are Q functions, and actually, this is the testing statistic for doing such evaluations. And this is another one is doing spatial temporal experiment and how to using Q functions. And actually this is double robust V functions, value function. Then how to estimate the average treatment effect for doing these kind of things. And there's different papers that we wrote. And actually this is the last section is about simulations. And actually we spend a lot of effort to do all these different methods. At the end of the day, and we want to basically come up kinds of simulators, because we don't want to do all the repeated same thing all the times. Okay, and actually we wanted to have simulators to help us to basically reel the marketplace. Okay, and actually we wanted to do visual marketplace simulators, basically simulate the marketplace interactions, basically how to simulate ordering, scaling, pricing, subsidy, and also give feedback to different strategies and speed up iterative the update of the strategies, because that's important. We want to do using we hope this simulator can apply to 80% of our kinds of new strategies, and only 20% of resources to do this kind of online the policies evaluation. And also we'll reduce the cost of the interaction between strategy and platform, and update the model offline, and predict external trends and the trends in the market, and develop strategy to prevent losses. But actually we use a lot of ideas from the generative, aggressive game models, and also imitative learning to do this kind of things. Okay, and actually when we started to do this kind of simulators, we started with one simple policy first. Okay, and then we apply to all kinds of the single policy at first. Then we try to, these days we try to integrate all the things together for all kinds of policy within interact with each other. And this is also use causal inference ideas, like for instance, for this particular case, we have the hidden these kinds of users recommendation policy, and also the hidden confounders unobserved. Okay, and I just go to the end of my talk. And actually, And for people who are interested in this kind of the method and actually the data, and actually we have already released some data sets connected in our platform through our Gaillard kinds of programs. So far, there's about more than 4,000 of applicants from the 660 university and the research institute from over 30 countries. And I hope you can join us and play with some of our data set. This is one of our data set you can play with. Okay. We have all kinds of data sets, okay, in our Gaillard programs, because if you want to do the computer vision, we have all these kinds of, we have the video data, you can play with that, and all kinds of data you can play with. Thank you.
Thank you very much, Tutu. You're very on time. Thank you so much. Wow, this is a fascinating talk. A lot of challenging problems and a lot of really modern flavor data science. And I'm so happy that you work in the front line of this all complicated problems, and like intersection of statistic, mathematics, optimization, and transportation. It's really fascinating. So hopefully that, as hope you mentioned, that in future we can have a bit more time given to you to have more sort of the details that you can, lecture. But anyway, good news is that Hansen is back. We lost him, and so he's back, and so go ahead, Hansen. So
okay,
we just your first slice, it was frozen, and then there was no moving on, and we decided to switch the order of speakers. But no, your turn. Go ahead.
Okay, thanks, Peter. Can you hear me?
You still have 30 minutes anyway, so just go ahead.
Thank you. Can you hear me?
Yeah, we can.
Okay, thanks everybody, and my sincere apology. I don't know why the system, it seems like it don't like me, it kicked me out. Okay. Anyway, I will move forward, and also I'm going to be very fast, quick. The story is very simple. So today I'm going to talk about something about deep learning, and I'm going to try to discuss one critical issue here, that is the learning rate specification. By simple method, we call the local quadratic approximation. So what is learning rate specification? I'm going to give a very quick and a simple introduction. So this is a work about deep neural networks. We know that this leads to a lot of fancy and successful applications, just like Hong has discussed, a lot of interesting applications. For example, we all know that deep learning and reinforcement-based method has achieved amazing achievement in a Go and all kinds of different games. And this is something like a security check system in the airport. And our team has done something about the Mahjong. Okay, let me double check. This time I'm still in the system, right? Nobody kicked me out, right?
You're still in the system. Yeah.
I'm already talking about 30 minutes. After the finish, I said, why Peter don't make any comments, right? Some that found that I have already kicked out. So anyway, those are very nice and interesting AI-related applications. What is standing behind this is one fundamental method called deep learning. Deep learning is a general terminology referred to a lot of models with a deep structure, okay? And it's the first, most important probably prototype is with deep structured neural networks. So this is one simple figure trying to show the idea of the neural networks. So what is this? If I treat this one output node as our Y and input node is our all kinds of X, okay? And every edge stand here, that means a nonlinear transformation about this particular input X feature is come to the output node. And so the output node Y collect a lot of nonlinear transformed features and do a linear transformation, linear combination to form the final output. So if we take every feature as one particular X and apply certain kind of like a random type of the nonlinear transformation, what we get here is looks like really like just a spline, okay? So in other words, we have to do a certain type of nonlinear transformation based on original X feature so that they allow very flexible output on this side. So it looks really like a nonlinear non-parametric regression. But probably one key difference is that this nonlinear regression model, they allow for many layers and that leads to a lot of very interesting findings. Okay, so as the general methodology and in terms of mathematical notations, I try to write it in this way. So whatever the model structure is simple or complicated. Basically, it is just a nonlinear transformation about an x. This transformation should depend on some kind of unknown parameter, which is called theta. After the transformation, we're trying to use to predict our y. The y could be continuous or could be binary. Then the next question is that how are you going to estimate the theta, right? Okay, there is always a simple question, simple answer to this. Very often I talk to my students in the class. If one day I ask you a question, how to estimate one particular parameter, how are you going to answer this question? There's always a simple answer. You just answer it, said maximum likelihood estimator. Very often it is correct. Same thing happens here. How I'm going to estimate this? Give a simple example. This is my input feature. X is the image, it's a photo. Okay, this is my X. Okay, and after reading this, I take this into my function, regression function. I'm going to make a prediction about this guy in the photo. It is a gentleman or it is a lady. Okay, and how I'm going to estimate the parameter theta? Basically, it's just the negative log transform the likelihood. So it's a maximum likelihood function. If you use the terminology in terms of TensorFlow programming, people call it categorical cross entropy, but that is basically just the log likelihood function. So by optimize this, we should be able to get an estimate for theta, right? The story seems to be very, very simple, okay? Now what makes it more complex, so complicated? Because we are facing certain kind of unique challenge here. Let's think about it. If I just run, like say, a generalized linear model, I try to optimize this likelihood function, okay? How am I going to do that? Suppose you have a 10,000 sample size and the feature dimension is like 10. This is a very standard situation. How am I going to do that? I'm going to use Newton-Raphson types of algorithm. How do I do that? I start from an initial estimator. For example, theta hat t, okay? And then evaluate the first order derivative of the loss function at this particular parameter s point. And then also evaluate its Hansen matrix, that is the second order derivative. And then plug in this formula. This leads to a standard Newton type of algorithm. This algorithm works very well. Okay, in fact, for most of our standard software and also our own developed programs, we're going to use this one. It works very well in the sense that first, it is not that sensitive to the initial estimator. Start from whatever reasonable initial estimator, they converge to the final value. Secondly, it converges really fast. It converges exponentially fast. After typical normalized 10 iterations, it converges to a very high precision. So it works very well. Because we have a Newton type method, so the user experience in terms of software usage is very good. No matter what kind of statistical software you're going to use, you are going to use R or SAS or Stata or whatever. You just tell the software set that I want to run a logistic regression model with data set like this. And the software say, yes, I got it. And then I'm going to give you the final estimation result immediately without asking you any single question, right? You give the software order, okay, supply the data, they give you the answer. That's a simple and a very pleasant user experience. But if you come to the deep learning, such type of nice experience disappears. You tell the software, like TensorFlow said, I want to fit this deep learning model. The TensorFlow will ask you another question back. They said, what kind of learning rate I actually use, right? What is learning rate? I'm going to tell you a little bit later, but that's something that I'm going to ask you. And you are going to decide what kind of learning rate you're going to use. Could be a very, very hard choice. And very often, it is subjectively decided, okay? So what is that? Okay, let's first look at what's the challenge we face for deep learning model. This is a very famous deep learning model called ResNet, residual network. This model achieved excellent prediction accuracy in a huge data set called ImageNet. And this model itself is of a huge dimension, okay? The input X feature probably not that high dimension, but the number of parameters used by this model is huge. Let's look at this. How many parameters they used? They used 25.5 billion number of parameters. So this is a huge number of parameters. If you stack the form of vector, this vector is extremely long. And in this case, certainly you cannot compute the Hansen matrix anymore, right? Because no computer in this world probably can save such a huge matrix. Even if you can save it, then the computation cost is to be extremely expensive. and you don't want to do that. Then how are we going to solve this problem? Anyway, we still need to optimize the loss function to find the final estimate. So this leads to the algorithm typically used in the deep learning practice. We call it stochastic gradient descent algorithm. It's kind of the secondary uncompromised algorithm. What is that? Okay, so let's say this is my whole data set, ImageNet. It's a huge data set with more than 14 million images. That is sample size more than 40 million. Okay, and we have a deep learning model like ResNet on that. I want to fit on that. How I'm going to do that? As we said, we cannot compute the Hansen matrix, right? We cannot compute the second order derivative, but I think we can still compute the first order derivative. Okay, if I cannot compute the first order derivative either, then I think this is a problem, hopeless. Nobody can solve it. So given an initial value, we try to compute the first order derivative for each sample data point. Totally, we have 40 million samples, 40 million photos. We do this for everyone and average them, right? This is what? This is a whole sample based first order derivative of descent direction, gradient direction. Okay, so by doing so, we know the gradient direction. We know this is the right direction to move on. You move along this direction as long as your step size is small enough. Theoretically, we can guarantee that the loss function is going to be improved. But improved by how much? That's another issue, right? So you have to ask the question, okay, I got the right direction, that is the gradient direction. But can you tell me how far away should I go, right? Given this particular direction, should I move a big step or small step or middle step? What should be the size of this step? This is a parameter, unfortunately, algorithm cannot decide. It has to be specified by the user. We call the learning rate, okay? Learning rate is terribly important parameter for practical optimization. If you specify it too large, okay, even for a loss function like least square linear regression, it might not converge. So even for problem as simple as linear regression, if the learning rate delta is too huge, the algorithm do not converge. So if you want to converge result, the delta should be small as possible. Unfortunately, if you are too small, the algorithm converge, but converge at a very slow speed. Okay, it takes you forever to wait for the final result. That's not pleasant either, right? So determining the optimal choice of the learning rate is very, very important. But this is not end of story. People find that even compute the first order derivative for such a huge sample size is still painful, right? How am I going to do that? They said probably we don't need to compute the derivative for the whole sample. Can we just do this computation for a randomly selected subsample, right? Then that leads to the stochastic gradient descent algorithm. That means this is my whole data set. Sample size is very huge. And then we draw some random subsample called S1. We compute the first order derivative on this subsample and move one step forward and then get the next subsample, another step forward, and another subsample, another step move forward, right? So this is called stochastic gradient descent. Stochastic means that we're doing random sample. Is this good method? No, I don't think so. I mean, this is a compromised method. If I have a supercomputer, I will not do this. But unfortunately, I do not have a supercomputer. Typically use the GPU that has very limited memory, okay? We cannot hold a huge data set in a graphical memory. So we have to do this. This is a common practice. So it is going to be a very, very slow progress. This was supposed to be a video, clip of video, but unfortunately I cannot show it for whatever reason. Let me show the key here. So this is an example with a 60,000 sample size. I make it into a total of 1,000 non-overlapping batches. Each batch contains 60 sample sizes, 60 images. Of course, you can make it 60 to be 100, 200, 600, anything, as long as your computer software, hardware support. Okay, I just want to make an example here. How does this work? Let me show you this. Okay, this is my whole data set, 60,000. I randomly shuffle them so that I have a random order and form a lot of batches. How many batches we have? For example, this is 1,000 batches. On each batch, I compute the gradient descent, okay? On the second batch, I computed the gradient direction again, go one step forward, and the gradient descent here, 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 here. After you do all the batches, we call this means that you finish the one epoch. Okay, so you do one epoch, second epoch, and so on like this. As I already done 21, 27. For sophisticated algorithm, it takes several hundred epochs to converge. That's a very typical thing. So it's painful and time consuming. As anything, we can speed up this process should be useful, even though this is very, very difficult. So traditional stochastic gradient descent has a lot of problems. Of course, this is unstable, right? Because your computer, you estimated the gradient direction based on a subsample. It's not stable, right? Then this motivated a lot of methods trying to stabilize it. And also, still, you need a subjective determination of the learning rate. Okay. Well, typical experience is that when you start your algorithm, you want to use a slightly larger learning rate so you can move fast, right? But once you reach a certain kind of stage, for example, you are already very close to the final solution. Okay, then you need to really fine tuning. In this case, the learning rate should be smaller, right? So you start from a relatively large tuning rate and then move it to smaller, 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 and so on. This is a subjective tuning process. Can we make it automatic? Okay, so as I said, this is one of the very, very important problems in the deep learning literature. So that method has been developed. Due to we have limited time, I cannot discuss every one of them. So I want to give a very quick review. Like this, they are trying to, you get a direct, you get the first order derivative at every iteration, every batch. You try to merge them together so that you can form a new estimator. It combines a lot of information from different batches, so the estimator is slightly more stable, right? But unfortunately, I probably is more biased also. And this is another method somehow use a second order derivative information. And those are some other methods. This is the method we typically very often use in the class, trying to teach students to use. This is the method that combines a lot of techniques, has been used in the previous method. Okay, so this is a method, in most cases, it works very satisfactory, but not necessarily the best one. In fact, I think the best one always is just the gradient descent method, but with a human-tuned tuning parameter. Okay, so let's look at all those methods. They are not automatic, right? They require human intervention with the software, with the machine interactively. Okay, start from every beginning till the end. Of course, they're not optimal in a sense. None of those methods can guarantee that the loss reduction they achieved in every step is optimal. Okay, nobody can do that. So we are going to solve this problem, try to give a solution. We propose a method called local quadratic approximation. So the key here is that first local, right? Because only locally we can try to approximate a function. A nonlinear function could be extremely complicated global-wise, but locally it's simple by Taylor expansion. Then we locally use a quadratic function to approximate it. Because why quadratic function? Because linear function do not have optimal solution in terms of loss reduction, right? And the cubic function, quadratic function, other function is too complicated. Quadratic function is a simple function. You have analytical solution for optimal solution. How am I going to do that? Okay. So we start from a benchmark gradient descent method. Okay. So it could be standard gradient descent method, could be momentum method, any method. They give us the direction to search. So this is the part I cannot improve so far. So we just take this from a benchmark method. Then we try to address a question, given this direction, already been specified the benchmark method, what should be the optimal tuning rate, optimal learning rate we should use, right? Okay, so we locally represent the loss function as a function of the learning rate delta. Delta is a scalar, it's not a high dimensional parameter. So it can be easily approximated by quadratic function. Same thing cannot be done if you do this for the original parameter. That's ultra high dimensional. That's terribly difficult. But if you do a local quadratic approximation for a scalar, that's a whole lot easier, right? So as long as you can get this coefficient, the linear coefficient A, quadratic coefficient B, okay, middle school mathematics can tell us what should be optimal solution for delta, right? That's it. And this delta is automatically decided by the algorithm, and it leads to almost the best loss reduction in terms of fitting process. Okay, but if not, so the key is that we need to get what is A and what is B. So I do some mathematical derivation. I run into a bad news. If I want to compute B, I still need to compute the Hansen matrix, right? That's not surprising, right? Because the Hansen matrix of the loss function determines the second order derivative along any direction, right? So if you want to get this coefficient B, you probably need to get the Hansen information for the whole loss function. That's terrible and painful. So I found another way to solve this problem. I said, I'm not going to compute this according to this formula. Instead of what? I solve an equation, right? Even though deep learning model is very complicated, so that its Hansen matrix is difficult to compute. Its first order derivative is also difficult to compute. However, the loss itself is easy to compute. The output loss is a scalar. It's easy to compute. So given the current step estimator, we do a small random perturbation. One is plus, one is minus. And then you got an equation on this side, right? All those loss function looks complicated, but can easily computed, evaluated by the software. And then once you got the equation, I can solve for A, solve for B. Once you get A and B, I got the automatic determination of the tuning parameter, the learning rate, okay, delta. So that's the way I get it. Even though the whole formula looks slightly more complicated, but if you look at it more carefully, this is the loss function, not a derivative, not a Hansen matrix. That's a key difference. So it's easy to compute. The computational cost is completely ignorable. And also because it's automatically decided. If you start from every beginning, your first, it can give you a relatively large step size. When you come to the stage, you have already been very close to the optimal solution. This number automatically close to 0. So the learning rate also automatically close to 0. This PPT was developed based on first draft. We're currently under revision for computer journal. And the referee asked us to do some theory. So theoretically, we can prove one thing under simple model, for example, linear regression model, that our proposed algorithm, LQ algorithm, converge to the optimal solution at the geometric speed. This speed, in terms of geometric speed, it is the same type of convergence rate as the standard gradient descent algorithm. However, the difference is that the contraction factor offered by LQA is smaller than the contraction factor of standard gradient descent algorithm. So that explains why it converges very fast. And also the nice thing is that no human intervention, right? The software will not ask you for the specification of the learning rate anymore automatically. So it is automatic, this is our merit. And also it's dynamic, right? As you move on from one epoch to another epoch, the optimal learning rate adjusted automatically. It is nearly optimal in a sense that leads to excellent reduction in the loss function. I call it nearly optimal because this optimal loss reduction is evaluated based on approximate quadratic function. So it is not the exact loss function. So still it's very excellent. So very quickly, I show everybody some experiment to save time. I have done a lot of experiment. I just show you the last one. This is an interesting data set called Cypher 10. Simply speaking, is the input is all kind of pictures. The output is 10 different classes, like airplane, birds, and so on. And let me show you. I think we have this, right? Cypher 10 data set. And we evaluate on the ResNet. This is a very complicated data set, very sophisticated structure, a huge number of parameters. So this represents the most complicated case in our experiment. Let's take a look. The red line is our loss function, okay? So as the time moves on, the number iteration increases, the algorithm improves, the loss function reduction is very fast, right? It is fastest. And another one is that compared with its competitors, the optimization result is very stable, comparatively speaking. Look at those curves. It's very, very bumpy, right? It's very, very bumpy. Those are the in-sample results because our algorithm is developed for optimization. Okay, the referee asked us to do out-sample comparison. I didn't have enough time to come up with a new figure here, but the result is excellent. In terms of out-sample focusing, the result still will outperform all the competitors. Okay, and those competitors are all standard gradient descent algorithms, SGD algorithms, but just with different learning rate. So you can appreciate why automatic determination of the learning rate is so important. You choose different learning rate, the performance is really terribly different. If you choose carefully, and if you're lucky enough, probably a performance like this is close to our performance. But if you're bad luck, you can run into this situation. Okay, so to summarize, we didn't offer a new method for new gradient descent direction. We didn't offer a method to come up with a second order like information like the Hansen matrix computation. We just offer a very cute and smart method to determine the learning rate. Okay, the learning rate is something truly useful and important for practical implementation of the deep learning models. So in terms of future research, there are a lot of interesting things we can do. For example, let's look at the dimensionality. Oh, we have a very ultra high dimensional parameter, like 20 million number of parameters. But so far this year, only one common learning rate. That's embarrassing and it doesn't make sense, right? Can we come up with some other idea so that we can allow different learning rates for different parameters? That's something interesting, right? And overfitting effects, according to our new experiment, it seems very okay, not a big deal. And also, I do believe giving 20 million parameters, got to be many number of parameters that actually should be zero. Huge sparsity should be there, right? But how to explore them, so far I don't have any idea. Okay, apologize again for being kicked out by the Zoom. I hope this time I didn't kick out again. Okay, thank you. That's all for today, for my talk.
Thank you, Hansen. Wow, you did a great
there, right?
job. You still have 6 minutes.
Oh, thank you.
Actually, there is a question. Since we have a little time, somebody is very interested in knowing the history of Gou Xiong Hui, and who is the Er Xiong? You are Da Xiong, right? Who is Er Xiong and your Gou Xiong Hui family? Yeah, can you tell us a little bit of the history?
Okay, thanks. Because this interest now started, can I say it in Chinese?
Sure. Yeah.
就是在商学院教书呢，有它一个比较有乐趣的地方，就是我们有2种学生，一种呢就是正常的这个统计学的博士生，还有一种呢是 MB 的同学，他俩非常互补。MB 的同学他有问题，他有业务问题，但是呢他可能方法论上是少一些。那统计学的老师和同学呢，他这方面多一些。然后我就组织了一个沙龙活动，把大家放在一起，都不是咱们这个比方统计学的老师讲，是请 MB 的同学讲他们公司都有什么好玩的事情，我们哪些可以学习了，他碰到什么挑战。然后这个沙龙我努力的办了几年啊，还挺好玩的，很多其他学校老师同学都来参加。那时候呢，我们就需要这个会议通知，整了个微信群，微信群呢取了个名字叫做我当时不会取名字，我取的叫大数据讨论班。然后里面有同学就给我提建议说这个汉生老师你的名字取得太土了，对吧？到处都是大数据，你也这么大都土不土？哎呀，我想想，我说你说的有道理，对吧？我说你帮我取个名字吧。他回去想了很久啊，过了几天告诉我说王老师，咱们叫什么英雄会怎么样？我听了当时就没乐翻掉，我说这个英雄谁批给你当的呀，对吧？当狗熊还差不多。然后我们俩就在那说着玩，后来我突然觉得好像狗熊还是比较可爱的，对吧？动画片里的狗熊都是傻傻的笨笨的，很正能量，也提醒我们自己对这个世界的无知需要学习。所以我就问那个微信群里的人，我们叫狗熊会怎么样？居然大家还都挺喜欢的，然后就把它叫开了。然后狗熊会现在的公号大概，因为狗熊会呢有时候像开玩笑说学习总是比较辛苦的，所以不大会有太多人关注狗熊会的公号。我们现在就大概14万多的这个粉丝，然后呢特别感谢 Peter 啊，这个给我们做的这个学术报告是第一个，也特别感谢后面还有这个朱基老师，很多老师给我们做过报告。所以狗熊会呢组织和分享了大量的学术报告，一学术报告多了吧，总会有人在那里不停的问问题，大家需要解答，所以我们需要一个这个老师或同事去解决这些事情，他又不想暴露他的这个，他又想保护他的 privacy， 对吧？我们就说叫熊二，所以熊二是我们的一个同事啊，然后这个全职的同事，然后他每天在里面各种各样的忙活着回答问题，所以简单的说，熊二就是我们的客服，大概是这样。
OK，
那个有个问题，那个大熊，那熊大那个有李阳问的问题，他说 ，Can this method be extended to finding optimal value hyperparameters jointly, such as learning rate and the number of estimates in an ensemble?
Yeah, that's a good question. I really wish to be able to do that, but so far. I cannot because the parameter dimension is extremely high. We are making one interesting progress is this, because we know that many ultra high dimensional data, they have a strong factor structure, right? you can represent as a low dimensional factor plus something else, which is high dimensional, but that high dimensional state is almost like the mutually independent across different components. So if that happens, we can jointly optimize the parameter and also learning rate in a very fast way. But that's something undergoing. But so far, that's the best we can have so far.
Okay, I think we move on for the sake of time. Thank you, Hansen. You gave an excellent talk. I think having one practice rehearsal was very useful, for sure. Okay, you gave an excellent talk. And yes, we need to rehearse our talk. Okay, good.
Thanks.
Yeah.
Thanks, Peter.
Yeah. So far we have heard 5 talks by senior professors. So in Chinese we call 前浪, 后浪, 后浪, 中浪, right? So now we now have a junior faculty, Dr. Jeffrey Zhang, and he's the third speaker of the second session. When I invite Heping to give a talk, and he said, "Oh, I could recommend another talent, junior faculty to replace me." People all know Mulan story in Chinese. This is a very famous Mulan story, 代父出征. So we have Jeffrey Zhang, who is doing this similar thing, 代父出征, to give this third talk of second session. He's currently worked at, he graduated from Princeton, got his PhD there in optimization, and now he works at CMU, Carnegie Mellon University. So Jeffrey, your turn. We cannot hear you, Jeffrey.
Okay, can you hear me now?
Yeah, we can hear now, yeah.
All right, well, thank you for the introduction. Thank you for having me. I don't really consider myself a leader in my field, but I do consider myself a leader in my work. Like Peter said, I work in optimization. I also do a little complexity theory. So I adjusted this talk. Hopefully this talk is better for a statistics audience. So this talk is going to be about local minima in polynomial optimization. So first, there we go. So what's a polynomial optimization problem? So we've all seen optimization problems. So these are problems where that are typically defined by having some sort of objective function, having some sort of constraints, and some sort of variables. And a polynomial optimization problem is when the when the objective function is some polynomial and the constraints are given by some polynomial inequalities. So these include cases like linear programming. So this is when the objective function and the constraints are all linear functions. There's some other very classical examples such as like 0-1 combinatorial optimization. But the point here is that polynomial optimization problems are very general. Any problem, for example, in NP can be modeled as some polynomial optimization problem. And what's really nice for me is that if you're a complexity theorist, polynomial optimization problems are really nice because you can actually define the problems very, very formally. And all the problems I'm going to talk about today are going to be related to local minima. So just to review what a local minimum is. We all know what the global minimum is. It's the point in the feasible set that has the best objective value. What a local minimum is it's not necessarily the global minimum, although any global minimum is a local minimum. But a local minimum can be more general. So these are points that beat other feasible points near it. So for example, if we have this problem here where these are the sublevel sets, this point here would be the global minimum, but we have some local minima here. So here we can see a point that is not the global minimum, but does beat all points near it an objective value. So why do we care about local minima? So probably the number one reason is that finding global minima is not easy. So there's this recent idea that, okay, we can maybe find local minima. And now, for example, there's this idea where you just run stochastic gradient descent, see what happens, and you end up at a local minimum. And this actually, and most of the research that goes into local minima in the machine learning field, a lot of it focuses on showing, for example, that any local minimum is a global minimum, or there's you try to show that the Hessian at any local minimum is non-singular. But there's a lot of work that goes into this, and what I'm trying to do is really try to understand local minima more formally from a complexity perspective. So just to review some of the literature on local minima in polynomial optimization. So this is the question of deciding local minimality. This is the question of I give you a problem and I give you a point, and I want to know whether it is a local minimum of that problem. So there's some cases that we do know how to solve. For example, if we have just some quadratic and we're trying to minimize it. For example, this is like least squares would be an unconstrained quadratic optimization problem. We do know how to tell if a point's a local minimum. Essentially, it just comes down to first and second order conditions there. And the same goes for linear programming. Like I said before, these are problems where the objective function is linear and the constraints are all linear. And then any local minimum is a global minimum. But there's also some intractable cases. For example, if you don't have any constraints, but you're trying to minimize a degree 4 polynomial, you actually cannot tell if any given point is a local minimum. There's essentially degenerate examples where the Hessian at local minima are not in fact non-singular. So you need to come up with some other checks. And the same goes for quadratic programming, which I will address more in this talk. Quadratic programs are problems where the objective function is quadratic and the constraints are all linear. And so this is just an outline of my talk. So I'm going to talk about local minima in polynomial functions, and then I'm going to talk about local minima in quadratic programs. And before I go on, I just want to talk about semi-definite programs just a little bit. Semi-definite programs are really the main computational tool for the first part of the talk. So what's a semi-definite program? So it's an optimization problem. Your objective is some linear function of your variables, and then your constraints are some linear functions of your variables, and you're also allowed to have some what are called linear matrix inequalities. So this is you impose the constraint that some matrix is positive semi-definite. So this kind of set here is what's known as a spectrahedral shadow. You can just think of it as spectrahedra if you know what that is. And semi-definite programs are essentially the most advanced conic optimization tool in optimization. But if you're looking for some applications closer to statistics, you can get the nuclear norm minimization, which is a very common heuristic used for low ranks matrix approximation. So for example, like the Netflix problem, you can use it in phase retrieval, and then there's some applications you can use it in what's called shape constrained regression. So this is where I'm trying to fit some function to some data, but I want some constraints on that function, such as, if I have like a car and I want to know what the price of that car is based on some variables, for example, like the mileage, I should expect that the car becomes less valuable the more miles on it. So I would want whatever function I fit to actually be monotonically, I would want the price to be monotonically non-increasing in the mileage. So that's kind of an example of what shape-constrained regression is. So just some more review of some things that are previously well known. There's some, there's really two questions that I'm going to address. So for a given polynomial, I want to know if a point is a critical point. So these are just points where the gradient vanishes, second order points. These are points where the gradient vanishes and the Hessian is positive semi-definite, a local minimum and a strict local minimum. So again, the question of interest is, if I have a polynomial and I give you a point, I want to know if it is one of these four types of points. And the other question of interest is, again, I give you a polynomial, and the question is, does that polynomial have one of these four types of points? So not all questions here are created equal. I'm sure that most people here, if given a degree 1 or 2 function, would be able to tell if a given point is a critical point or second order point. This is a year 1 multivariable calculus exercise, but there are a lot of problems here that are not as trivial. So, so before I came along, essentially, these were the cases that were left open by the literature. And then these are essentially what I'm actually going to focus on in this talk, these cases here. So as you can maybe see, I'm going to end up talking a lot about cubic polynomials. And one thing I just want to point out here is that, as you can see, that deciding whether a degree 3 polynomial has a critical point is NP hard, but deciding whether it has a second order point is somehow easier. So that might be unintuitive, and it probably is a little unintuitive, but essentially there's some algebraic geometry that goes into it, and I'm going to go more into that later. So I'm just going to quickly go over this square here. So for a given polynomial, that's degree 3, is a given point a local minimum. We have a condition, it looks like this. So if you have a point that satisfies the first and second order necessary condition, then there's this third condition that can be checked in polynomial time that will tell you if a point is a local minimum. So here, this n notation means the null space of some matrix, and then this subscript 3 notation means the cubic component of that polynomial, so it's just the terms of degree 3. And really the thing to focus on here is that you should really be looking at the null space, and the proof is done by double Taylor expansion. So this is just to say that there is this nice condition that can be checked in polynomial time. But really the more interesting question is, can we actually find local minima? So again, the question is, given a cubic polynomial, can we actually find a local minimum of it? So if you took, say, multivariable calculus, maybe something you would try is you search for a critical point. Unfortunately, deciding if a cubic polynomial has any critical points is NP hard. And it really comes down to the fact that the gradient of a cubic polynomial is this vector of degree 2 polynomials. And then the quadratic satisfiability problem is really one of these classic NP hard problems. So are we dead? Does this mean we can't find local minima? So really just what this means is that maybe we should try something other than searching for critical points. In other words, maybe something that isn't gradient descent. So like I said before, the main tool that is going to be used in this part of the talk is semi-definite programming. And really the approach that I'm doing here is I have a non-convex problem. Again, because I'm searching for the solution to some quadratic satisfiability problem. So what we're going to do is we're going to make our problem convex. There's some hidden convexity in this problem that actually is very, very elegant. So something that is not entirely trivial to prove but ends up being true is that the local minima of any cubic polynomial forms a convex set. So it also turns out that cubic polynomials are the maximum degree polynomial for this is true. So for example, here's a really simple degree 4 polynomial. There's some local minima, and it's a non-convex set. And then we just have an example here of some cubic polynomial. These are the critical points. As you can see, the critical points form a non-convex set. This is maybe what you should expect. In general, that the set of critical points should not generally form a convex set. But what actually happens is if I look only at the critical points where the Hessian is positive semi-definite, I actually do end up with a convex set. And in this particular example, these points here are the local minima of this particular polynomial. So the set of local minima of any cubic polynomial is a convex set, but actually you can say something a lot stronger about these functions. The local minima of any cubic polynomial is actually a spectrahedral shadow. So so just to put this in perspective, the set of local minima of any quadratic polynomial forms a polyhedron. So that's a set that's defined by a set of linear inequalities. Again, that just follows because the gradient of any quadratic polynomial is linear. So then its critical points satisfy some linear inequalities. So the local minimum of any cubic polynomial is actually a spectrahedron, essentially. So local minimum of quadratics are polyhedra, local minimum of cubics are spectrahedra. And it actually goes in the other direction too. Any spectrahedron you can essentially write as the local minima of some cubic polynomial. And if you're someone into SDPs, the implication here is actually that semi-definite programming is at least as hard as finding local minima of cubic polynomials. So how do we actually find local minima? So again, the approach here is to find some hidden convexity in our problem. So we're going to look at this problem here. So I'm going to minimize my cubic polynomial. So in general, actually, a cubic polynomial is in general not a convex function. But what I'm going to do is I'm going to restrict the feasible set to this set here. It's the set of points where the Hessian is positive semi-definite. So you can think of this as the set of points where my function looks convex. And then I am minimizing my I am minimizing my non-convex function over the set of points where it looks convex. So essentially the idea is that my function is actually convex over the feasible set. And the other thing here is that the set of points where the Hessian is positive semi-definite is for a cubic polynomial convex. The reason for this is that if I have a degree 3 polynomial, I take its second derivative, I end up with a matrix which is linear in the variables of the problem. So I actually get a spectrahedron. Spectrahedra are convex. So what I end up with is a problem over a convex set where my objective function is essentially convex over that set. So just like, for example, for a univariate function, what it would look like is the set of points where the function looks convex is here. And if I minimize the cubic polynomial over this particular set, I actually end up with the local minimum of this cubic polynomial. But how do we actually solve this problem? So it turns out to be with semi-definite programming. It's the tool we use is something called the sum of squares relaxation. Don't worry about what that is. The end goal here is to actually show that the set of second order points is semi-definite representable, which means that I can write it as the feasible set of some SDP. And these are just some of the tricks and techniques that are used in the proof. And eventually we end up with a theorem that looks like this. So don't pay attention to the math down here. You can go ahead and just check that everything here is linear in the decision variables, and this is a linear matrix inequality. But the main observation to make is that yes, this set here is in fact the feasible set of some semi-definite program. So in fact, the set of second order points of any cubic polynomial I can write as the feasible set of some semi-definite program, and this semi-definite program I can actually get directly from the cubic polynomial itself. I don't need to do any optimization or no nothing. Just give me the cubic polynomial and I can give you an SDP representation of its second order points. And then if I just want to get the local minima, there's this geometric relation between the two. The set of local minima is the relative interior of the set of its second order points. So what does that mean? So if I imagine just like a piece of paper in R3, I can think of that piece of paper as essentially a two-dimensional object in three-dimensional space. It doesn't actually have an interior. But if I think of that piece of paper as a two-dimensional object in two-dimensional space, it has an interior, and then I just bring that interior back up to three-dimensional space, and that's what's known as the relative interior. And there's this simple technique where you can find the relative interior of a point in that set. What I do is I take my set, I find what the largest and smallest point is along some direction. I pick any value between them, and then I find the largest and smallest value in the set along some other direction. I pick some, and then I find the largest and smallest value on that direction. I pick something in the middle, and then you can show that this procedure here terminates with a point in the relative interior of the set. So just a quick takeaway from this part of the talk. Even though it's NP hard to see if a cubic polynomial has a critical point, if you throw in some algebraic geometry, what you can do is you can actually find some hidden convexity in your problem. And a problem that might seem hard to solve at first glance actually does turn out to be tractable. So in about the 2 minutes left, I'm going to talk about, unfortunately, a negative result about local minima in quadratic programs. So this is a question, this is from 1992, which is given a quadratic program. Again, these are problems where the objective function is quadratic and the constraints are linear. The question is, can you find a local minimum of a problem like this? So it's been shown that it's NP hard to decide if a point is a local minimum of this sort of problem here, but the question is, can we actually find a local minimum? There's not actually any implication between the two. So what we've shown is that it's not only hard to find a local minimum, it's hard to find a point even close to a local minimum. So for any constant c, you can't actually find a point within distance c to the n of a local minimum of that problem. So again, this is really to say that beware of any claims that any algorithm can find a local minimum of your problem, because if they do, they might really be onto something big here. The reduction is from the stable set problem. Don't worry too much about what that is, but just some more NP hardness results that came as part of the proof. It's NP hard to decide if a degree 4 polynomial has a local minimum. And then the same is true for a quadratic program. So if I have a quadratic program, I can't necessarily even tell if it has a local minimum. But again, here the question specifies that the feasible set is bounded, which means that there always is a local minimum if the feasible set is bounded. So what you do is you take this result that you can't actually tell if a polynomial has a local minimum. And what we do is we construct a very specific polynomial that if it has a local minimum, it is at the origin. And then we just take that polynomial, stick a bound on it, and then what happens is either there's a local minimum at the origin or any local minimum is on this boundary that you just added. So there's actually a separation between the two. So essentially any point close to a local minimum is either here or here. And that's essentially is essentially the 2-minute idea behind this reduction. And I'm out of time.
Jeff, you have 5 minutes. You still have 5 minutes.
Yeah, but that's for questions.
Oh, I see. Yeah. Yeah.
This is supposed to be a 25-minute talk.
Yeah. Yeah. If you want to leave 5 minutes for questions, that's even better. Yeah. Great.
Yeah, so I have the 5 minutes for questions. I can also just go into actual detail on any part of the talk.
Up to you. Yeah, which way?
Tell us exactly, did you answer the question that somebody posed in 1992?
Yeah, so this is the question. So this is the answer. So again, the question is, what's the complexity of finding a local minimizer, assuming the feasible set is compact? And our answer is you can't even, so first of all, you can't even find a point. And then what we have is a stronger result saying that you can't even get exponentially close to a local minimum. So like, for example, this C could be a 2, and the result says that unless P equals NP, you can't find a point within Euclidean distance 2 to the n of your problem, which is a very, which is essentially like hopelessly far.
I have a maybe naive question.
So tell us your name.
Oh, my name is Yufeng Liu at UNC Chapel Hill. So my question is, does it mean if I want to solve a quadratic programming, if it's not convex, so there's really not much guarantee I can do using any existing software?
Yeah, exactly. So essentially existing softwares, they're mainly built on heuristics. Usually when you have a problem, like I said, especially in machine learning, there's a lot of work that goes into showing that your particular problem has the property that local minima are like easy to verify. For example, something recently has been known as like the strict Zabo property that essentially says that any local minimum has a non-singular Hessian. So it's easy. So if your Hessian is non-singular at a second order point, then you definitely are a local minimum. But the issue is you can construct a lot of degenerate examples where local minima do not necessarily have Hessians that are non-singular. So in a lot of problems, this, if you just throw a random problem in, probably all the local minima are nice in this regard, but you can construct like interesting examples where this is not the case. But yeah, in general, quadratic programming is NP hard. There are solvers, but they might take like exponentially long time in the worst case.
That's very useful to know. I know that in non-convex optimization community, obviously global is out of reach. Local minimum is also difficult, as similar as you were describing for this problem. So there's some work trying to study different type of stationary points. Is there any guarantee in the sense of local minimum versus stationary point, how good for a particular problem? I don't know whether that's a good question, but I guess what I mean is that if local minimum is out of reach, we have to sort of relax what we can find and trying to find some property of those. And stationary points are the next step, right?
Yeah, so like I kind of said earlier in the talk, even if you have a degree 3 polynomial, stationary points are even already like out of reach. And then there's always this issue where your stationary points could be saddle points, which is no good. But again, a lot of research in the machine learning community goes into showing that problems are nice in that local minima are, there's all these papers that say in the abstract, like, there are no spurious local minima. First of all, any local minimum is a global minimum. There's also a lot of papers that say in the abstract, like we also show that this problem satisfies the strict saddle property, which is something else that would make all these concerns about hardness like not apply in that particular problem. But the issue there is that you have a problem, and then for every problem, you need to put in the work into showing that under some statistical guarantees with like high probability, I get this property that my local minima are nice. And then, it's good, it makes for good papers, but is that really something you want to be your main go-to strategy in looking for local minima?
Great discussion. For the interest of time, I have to cut because we are already like 12 minutes after the scheduled time. So this evening we had 6 excellent talks, and I'd like to thank all the speakers of the workshop on behalf of the audience. And I hope that the 3rd Leaders Workshop next year, 2021, will be in-person conference. Maybe take a one-day program so that each speaker could have a little bit more time to, give a little bit more details. But in this very difficult period of time, we still have this opportunity to gather together and sort of share some of the ideas. I think all the 6 talks are so sort of the research in the frontier. I learned a lot and a lot of interesting problems. And like Dr. Sen said, there's a paradigm shift that statistics is undergoing a very major sort of reformulation of this discipline and optimization, data science, and everything coming into statistics. So I think we have seen quite a bit this evening from the 6 talks. Thank to all of you for attending the workshop on Saturday evening or Sunday morning. And then, this is your weekend. And so I hope that you can continue enjoying your weekend. Have a nice weekend. So I have to end the workshop now. So if you have any questions and something that you can email the speakers directly. And hopefully we can see you next year at, the the leaders workshop somewhere. Just pay attention to the announcements of this workshop in next year, 2021. Thank you. Take care. Have a very nice Sunday morning or Saturday evening. Yeah. Goodbye.
Peter, may I make a suggestion?
Sure.
Whoever can open your video, see if we can take a screenshot of everyone's face.
Oh, okay.
Yeah, everyone opens the video, see how many we can get up there.
Yeah, we still have 79.
Still 79?
They cannot
to see faces.
Yeah, we probably cannot fit into one screen.
While you're trying, I'd like to take the opportunity to thank Peter for putting this together and all the speakers actually the last minute.
Yeah, so hoping you are very good at taking photos. Do you want to take photos?
Let me try. So let's see this.
We have about 4 pages of attendees, and so it's very amazing that you know, through the cables that we can see each other and different time zones, and you know, and
the second page is all the just 1 second. For the picture to come up. Okay, 1 second. I already took the first page.
This is okay. You move to second page.
And then on the second page, I just see a lot of names.
If you feel comfortable, you can turn on your video.
Yeah.
Oh, Yugo. Nice to see you.
Okay, whoever willing to turn on your your videos, it's time to turn on so that I can take the pictures.
Yeah.
For the second page.
Yeah.
Okay, I'm gonna take it.
Jayang, very good suggestion. Yeah. So yeah.
I think different screens would have different pages, right? Your picture.
Yeah, actually, first page is complete full of pictures.
We have 4 pages.
Yeah, I know, but the second page, my screen is really large, but second page, I only have like 1/4.
Well, the question here is your job done or not?
Can you just do a screenshot rather than using a camera?
I just use my camera, but actually most people just leave it in there and it's okay. Yeah, let me take one more time. All right. All right. Okay. I think.
Okay.
Thank you so much.
Thank you so much. Take care.
See you next time.
Nice weekend. Yeah. See you next time.
Bye.
Bye-bye.